Hello and welcome back. Tonight we're traveling to the one place in the universe that humanity has known intimately for all of recorded history, yet somehow still barely understands. We're going to spend time with our moon, that pale companion that's been watching over Earth since before there were eyes to see it, before there were oceans to reflect its light, before there was anything we'd recognize as home. The moon is close enough that you can see its mountains with a decent pair of binoculars. It's the only world beyond Earth that human beings have ever touched with their own hands. And yet, it holds mysteries that we're only beginning to unravel. Before we begin, if you enjoy falling asleep to these cosmic explorations, a like or a comment helps other people find their way here too. And if you subscribe, you'll have a new place to rest your thoughts whenever you need it. But no pressure. You're welcome here either way. Now let's begin. The moon is Earth's only natural satellite, orbiting our planet at an average distance of about 238,855 miles. That number sounds precise, doesn't it? And it is, in the way that averages are. Though as we'll discover, the moon doesn't stay put at exactly that distance. It moves closer, then farther, in an elliptical dance that's been going on for billions of years. What strikes me about this distance is how perfectly calibrated it feels, close enough that we can see the moon's features with remarkable clarity, close enough that it tugs on our oceans and creates the rhythm of tides, but far enough away that it remains other, distant, a place we had to dream about reaching for millennia before we finally could. Light itself takes 1.3 seconds to travel between the moon and Earth, a tiny lag, but a real one. When you look at the moon tonight, you're seeing it as it was just over a second ago. In the grand scheme of cosmic distances, 238,055 miles is nothing, barely a whisper of space. And yet for most of human history, it might as well have been infinite. Here's something you might not know. The moon is leaving us. Slowly, gradually, at a rate of about 1.5 inches per year, the moon is drifting away from Earth. It doesn't sound like much, does it? 1.5 inches, the length of a bottle cap. But time is patient, and those inches accumulate. Every year, the moon is a little farther. Every century, a little more distant. Millions of years from now, long after we're gone, long after everything we've built has crumbled, the moon will have drifted so far that it can no longer completely cover the sun during an eclipse. Total solar eclipses, those rare moments when the moon slides perfectly in front of the sun and day becomes twilight, will eventually become impossible. The moon will simply appear too small in the sky. Future beings, if any exist, will look at our photographs of eclipses the way we might look at ancient fossils, evidence of a world that no longer exists. The moon is leaving us, not quickly, but inevitably. It's one of those slow cosmic truths that makes you feel the weight of time. The same side of the moon always faces Earth, always. This phenomenon is called tidal locking, and it means that for the entire history of human civilization, we've only ever seen one face of our companion. Think about that for a moment. Every person who has ever looked up at the moon, every ancient stargazer, every poet, every child lying in the grass, has seen the exact same hemisphere, the same patterns, the same Maria, those dark patches early astronomers thought were seas, the same bright highlands. There's an entire other side of the moon that remained hidden from human eyes until 1959, when a Soviet spacecraft finally photographed it. For billions of years, that far hemisphere existed in complete privacy, unseen by anyone or anything on Earth. Tidal locking happens because the moon's rotation period matches its orbital period almost exactly. It takes the moon about 27.3 days to orbit Earth, and it takes precisely the same amount of time to rotate once on its axis. So as it orbits, it turns at just the right speed to keep the same face pointed toward us. It's as if the moon and Earth are dance partners, locked in a gravitational embrace, moving together in perfect synchronization. People often call the far side of the moon the dark side, but that's actually a misnomer. The far side of the moon receives just as much sunlight as the side we see from Earth. It's not dark in the sense of being shadowed or unlit. It's only dark to us because we never see it. The term far side is more accurate, though admittedly less poetic. When Pink Floyd named their album The Dark Side of the Moon, they weren't being astronomically precise, but they captured something true about the human imagination. There's something about an unseen place, a hidden hemisphere, that feels dark to us. Unknown, mysterious, slightly ominous. But if you were standing on the moon's far side during lunar day, the sun would shine just as brightly as it does on the near side. The stars would wheel overhead. Earth would never rise above the horizon, forever hidden from view. You'd be more isolated from home than any human has ever been. The far side isn't dark, it's just far. But sometimes distance creates its own kind of darkness. The moon has no atmosphere, none. No air, no wind, no weather, no sound. On Earth, we're so used to the constant presence of atmosphere that we forget it's even there. The air carries sound waves from your voice to someone else's ear. It scatters sunlight and gives us blue skies. It protects us from meteors and radiation. It erodes mountains and shapes coastlines and makes the clouds that bring rain. The moon has none of this. If you clapped your hands on the moon, you'd feel the impact, but you'd hear absolutely nothing. The vacuum would swallow the sound before it could travel. The sky would be black even at noon because there's no atmosphere to scatter light. The sun would shine harshly, and the stars would be visible right beside it. And because there's no wind, no rain, no erosion of any kind, nothing on the moon's surface ever gets worn smooth. The footprints left by Apollo astronauts in 1969, 1970, 1971, and 1972 are still there, perfectly preserved. They'll remain for millions of years, long after every trace of those astronauts' lives on Earth has vanished. The moon remembers. Without an atmosphere to erase anything, it keeps a record of every impact, every visitor, every mark made on its surface. It's a museum of its own history. The moon's gravity is only about 1/6 as strong as Earth's. If you weigh 180 pounds here, you'd weigh just 30 pounds on the moon. You'd feel impossibly light. Every movement would require recalibration. The astronauts who walked on the moon developed a peculiar bouncing gait, part walking, part hopping, because normal walking didn't quite work in the reduced gravity. They'd push off and float for a moment before coming back down. You could jump about 6 times higher on the moon than you can on Earth. A modest vertical leap here might take you 10 or 12 feet up there. Not flying exactly, but close enough to feel like a superpower. But this lightness comes with a cost. Without strong gravity to hold an atmosphere, the moon can't retain gases. Without an atmosphere, there's no protection from radiation or temperature extremes. The very thing that makes the moon feel like a place where you could bounce and play is the same thing that makes it inhospitable to life as we know it. Gravity shapes everything. On Earth, it keeps us grounded, literally and metaphorically. On the moon, its weakness creates a world both liberating and lonely. The moon formed approximately 4.5 billion years ago, shortly after Earth itself. It's been our companion for almost the entire history of our planet. 4.5 billion years is a number too large to truly grasp. If you counted one number per second, never sleeping, it would take you more than 140 years just to count to 4.5 billion. And that's just in seconds. We're talking about billions of years. The moon has been there, orbiting Earth, since before the continents existed, since before plate tectonics began, since before the first oceans formed. It witnessed Earth's entire transformation from a molten hellscape to the blue-green world capable of harboring life. Every living thing that has ever existed on Earth has existed under the moon's watch. Every species that ever evolved did so with the moon pulling on the tides. Every night that any creature ever experienced was lit, at least partly, by reflected sunlight from that same ancient companion. The moon is older than rocks, older than water, older than life itself, and yet there it is, every night, looking exactly as it has for eons, familiar, constant, home. The leading scientific theory for how the moon formed is called the giant impact hypothesis. The story it tells is almost impossibly violent. About 4.5 billion years ago, when Earth was still young and forming, a Mars-sized object, scientists call it Theia, collided with our planet. Not a glancing blow, but a catastrophic impact. Theia was obliterated. Earth's outer layers were vaporized. Unimaginable amounts of material were blasted into orbit. For a time, Earth had a ring system like Saturn's, made of molten rock and debris. Gradually, over millions of years, this material began to coalesce, pulled together by its own gravity. It formed a new world, our moon. This means the moon is made partly of Earth and partly of Theia. It's a child of violence, born from destruction, forged from the remnants of a collision that would have sterilized any life that might have existed. But from that catastrophe came something stable, something that would eventually help make Earth a habitable world. The moon's formation was an act of cosmic brutality that somehow resulted in quiet nights and ocean tides and the soft light that falls gently through your window. Perhaps that's true of many things. Sometimes the most terrible events create the conditions for something beautiful. The moon is the 5th largest natural satellite in our entire solar system. Only 4 moons are larger: Jupiter's Ganymede, Callisto, and Io, and Saturn's Titan. It's interesting to think about this ranking. In absolute size, the moon is nothing special, reasonably large, but not exceptional. Ganymede is bigger than the planet Mercury. Titan has a thick atmosphere and liquid methane lakes. Io is the most volcanically active body in the solar system, constantly reshaping itself. But context matters. Relative to Earth, the moon is unusually large. Most planets have tiny moons, barely worth mentioning. Earth is not a giant planet like Jupiter or Saturn, yet it has this substantial companion, large enough to affect its rotation, stabilize its tilt, and create dramatic tides. The Earth-Moon system is strange. It's not quite a planet and its moon. It's more like a binary system, 2 worlds dancing together. Some scientists even argue we should call them a double planet rather than a planet and its satellite. We take the moon for granted because it's always been there. But in the context of the solar system, it's actually quite unusual. We're lucky, in a sense, to have such a prominent companion. Many worlds orbit their stars alone. The moon's surface area is roughly equal to the combined area of Africa and Asia. That's about 14.6 million square miles of terrain. Imagine for a moment trying to walk across Africa. Then imagine walking across all of Asia. Then imagine doing both. That's how much moon there is to explore. And yet, humans have only visited 6 locations on the lunar surface. 6 small sites, all relatively close to each other on the moon's near side, all chosen because they were flat and safe for landing. The Apollo missions didn't venture to the poles, or the far side, or the massive impact basins, or the strange magnetic anomalies, or the lava tubes that might be large enough to contain cities. We've barely scratched the surface. Most of the moon remains exactly as it's been for billions of years. Untouched, unexplored, waiting. 14.6 million square miles. Landscapes we've never seen up close. Craters that might contain ancient ice. Caves that might shelter future astronauts. Mysteries buried in rocks that have sat undisturbed since the solar system was young. The moon is small compared to Earth, but it's vast enough to hold countless secrets, and we've only just begun to look. Temperatures on the moon swing between extremes that would be unimaginable on Earth. In direct sunlight, the surface can reach 260 degrees Fahrenheit. In shadow, it plummets to negative 280 degrees Fahrenheit. That's a difference of 540 degrees. On Earth, the most extreme temperature variations from hottest to coldest are maybe 200 degrees, and that's comparing the scorching deserts to Antarctic winters. The moon experiences nearly 3 times that range in the span of a single day-night cycle. Without an atmosphere to distribute heat, every bit of the moon's surface is at the mercy of direct exposure. Where sunlight hits, temperatures soar hot enough to boil water instantly, if there were any liquid water to boil. Where shadows fall, the cold is deeper than anything you'd find even in the most remote corners of our planet. This is what happens in a vacuum. Heat can't spread through air because there is no air. It can only radiate directly. So the sunny side bakes while the shadowed side freezes, with no middle ground, no temperate zone, no comfortable in-between. The Apollo astronauts' spacesuits had to protect them from both extremes simultaneously. One side facing the sun, one side facing the darkness. Standing in a place where the temperature difference between your front and your back could be hundreds of degrees. It's a reminder that the moon, despite its familiarity, is an alien world. Hostile, unforgiving, beautiful precisely because of its extremes. The moon has moonquakes, seismic activity similar to earthquakes, though generally much weaker. The Apollo astronauts left seismometers on the lunar surface, and those instruments detected thousands of tiny quakes over the years. Some are caused by meteorite impacts, which makes sense. Rocks from space slamming into the surface would certainly make it shake. But others originate deep within the moon's interior, suggesting that something is still moving down there, still settling, still active in some small way. There are also thermal moonquakes caused by the extreme temperature changes at sunrise. The surface expands as it heats up, and that expansion creates stress, releases energy, makes the moon tremble slightly. But here's what's strange. Moonquakes last much longer than earthquakes. On Earth, a quake might last a few seconds, maybe a minute if it's particularly strong. The ground shakes, the energy dissipates, and it's over. On the Moon, a single quake can reverberate for hours. Why? Because Earth's interior is somewhat pliable, with layers that can absorb energy. The Moon's interior is cold and rigid. When it rings, the vibrations just keep going, bouncing around inside like sound in an empty room with hard walls. So the Moon doesn't just shake, it reverberates. It remembers the impact long after the initial disturbance. Even in its seismic activity, the Moon holds on to things, preserves the evidence of events, refuses to let them fade quickly. The Moon has no magnetic field today. If you brought a compass to the lunar surface, it would be useless. The needle would drift aimlessly, pointing nowhere. And yet, rocks brought back by the Apollo missions tell a different story. They contain magnetized minerals, frozen in place, pointing in directions that suggest they formed in the presence of a strong magnetic field. These rocks are old, billions of years old, and they remember something the Moon has forgotten. The Moon once had a magnetic field, perhaps as strong as Earth's is today. It must have had a churning, molten core, generating magnetism through the same dynamo process that protects our planet. But something happened. The core cooled, the dynamo shut down, the magnetic field collapsed, and now the Moon is defenseless against the solar wind, cosmic rays, and all the radiation that streams through space. Scientists don't fully understand why the Moon's magnetic field disappeared. Its small size means its interior should have cooled quickly, but the timing doesn't quite add up. Some rocks suggest the field persisted longer than it should have been possible. Maybe there's something about the Moon's interior we don't understand. Maybe the collision that formed it left it with unusual heat distribution. Maybe there are mysteries in its core that we haven't even begun to uncover. The Moon keeps its secrets. Even the rocks we've brought home don't tell us everything. When you look up at the Moon, you see patches of brightness and darkness. The bright areas are called highlands, ancient, heavily cratered terrain covered in light-colored rock. The dark patches are called Maria, which is Latin for seas. Early astronomers, looking through primitive telescopes, thought these dark areas might actually be bodies of water. It made a certain kind of sense. If the Moon had land, why not seas? If it had mountains, why not oceans? But the Maria aren't water. They're vast plains of solidified lava, frozen in place billions of years ago. The dark color comes from iron-rich basalt, the same kind of rock that forms much of Earth's ocean floor. These lava flows are old. Most of them formed between 3 and 4 billion years ago. And yet, compared to the highlands, they're actually relatively young. The highlands are the Moon's original crust, dating back to when the entire surface was molten. The Maria came later, flooding low-lying areas where asteroid impacts had cracked through the crust. So when you look at the Moon, you're seeing two different eras of lunar history. The bright highlands are ancient beyond ancient, witnesses to the solar system's violent youth. The dark Maria are merely old, marking a period when the Moon still had some volcanic activity, some residual heat from its formation. It's a face marked by time, wearing its history openly, showing us the passage of billions of years in patterns of light and shadow. Those Maria, those dark seas, were created by volcanism. Billions of years ago, massive asteroid impacts cracked the moon's crust. The impacts were so powerful that they broke through to the molten rock beneath, and slowly, over time, lava welled up from the interior and flooded the impact basins. The lava flowed like water, filling the low spots, creating vast plains hundreds of miles across. Then it cooled and solidified, turning into the dark basaltic rock we see today. This happened multiple times in multiple locations. Each mare, the singular of Maria, represents a separate event, a separate outpouring of the moon's interior onto its surface. Some Maria are circular, clearly showing their origin as impact basins. Others are irregular, formed by lava that flowed into connected depressions. What's remarkable is how long this process took. The Maria didn't form all at once. Different Maria formed at different times, spread across hundreds of millions of years. The moon was slowly bleeding out its internal heat, one lava flow at a time. Eventually, the volcanism stopped. The moon's interior cooled enough that magma could no longer reach the surface. The Maria are the last gasp of the moon's geological activity, frozen memorials to a time when our companion was still, in a sense, alive. Now those lava plains just sit there, cold and silent, preserving the memory of ancient fire. The largest crater on the moon is called the South Pole Aitken Basin, and it's immense, about 150 miles across and over 8 miles deep in places. To put that in perspective, that's wider than the distance from New York to Denver. If you were standing in the center of this crater, the rim would be beyond the horizon in every direction. You wouldn't even know you were in a crater at all. It would just look like a vast, slightly depressed plain, stretching endlessly. This basin is one of the largest impact craters in the entire solar system. Whatever hit the moon to create it must have been enormous, traveling at incredible speed. The collision would have been catastrophic, sending shock waves through the entire lunar body, possibly even through to the far side. The South Pole Aitken Basin is also incredibly old, probably over 4 billion years. It's been there since the early days of the solar system, when giant impacts were much more common, when the planets and moons were still being bombarded by the leftover debris of their formation. Scientists are fascinated by this basin because it's so deep that it might expose material from the moon's mantle, the layer beneath the crust. Studying it could reveal secrets about the moon's interior composition, about how it formed, about what it's made of all the way down. But it's remote, difficult to access, dangerous to land in. So for now, the South Pole Aitken Basin remains largely unstudied, a scar from the ancient past, waiting for the day we return with better tools and braver missions. The moon has water, not oceans, not rivers, but water nonetheless. Frozen ice hidden in permanently shadowed craters near its poles. For a long time, scientists thought the moon was completely dry. The Apollo samples contained no water. The extreme temperature swings and lack of atmosphere meant any water should have evaporated into space billions of years ago. But then we looked more carefully. We sent orbiters with sensitive instruments, and we found evidence of ice, significant amounts of it, tucked away in places where sunlight never reaches. Near the lunar poles, there are craters so deep, and the sun's angle so low, that the bottoms of these craters exist in permanent shadow. They've been dark for billions of years, and in that darkness, it's cold enough for ice to survive. ice delivered by comets and asteroids over eons, accumulated grain by grain, preserved in the eternal cold. This ice is precious, not just scientifically, but practically. Future lunar bases could use it, melt it for drinking water, split it into hydrogen and oxygen for rocket fuel and breathable air. The moon's ice could make sustained human presence there possible, could make the moon a stepping stone rather than a destination. So the moon isn't quite as dead and dry as we once thought. Even in the harshest environment imaginable, water found a way to persist, hidden in shadows, waiting. Some of these permanently shadowed craters have been in complete darkness for billions of years. Not millions, billions. Think about that. While Earth went through its entire history, while continents formed and broke apart, while life evolved from single cells to the entire biosphere, while dinosaurs rose and fell, while humans emerged and built civilizations, these craters remained in absolute darkness. They're some of the coldest places in the solar system, even colder than Pluto's surface in some cases. Without any sunlight, temperatures there drop to about minus 400 degrees Fahrenheit. At those temperatures, ice doesn't just freeze, it becomes rock hard, stable, nearly eternal. Volatile substances that would normally evaporate or break down can persist for geological ages. These craters are cold traps, preserving whatever falls into them like a deep freeze preserves food. Scientists sometimes call them time capsules because the ice and other frozen materials might contain clues about the early solar system. Comets and asteroids have been delivering water and organic molecules to the moon for billions of years. And in these shadowed craters, those deliveries are preserved exactly as they arrived. It's strange to think about. While you were born and grew up under the light of the sun, while you've experienced thousands of sunrises and sunsets, there are places on the moon where the concept of day and night is meaningless. Just endless, cold, unchanging darkness. Until, perhaps, a human brings a light there for the first time. The moon creates Earth's ocean tides through the force of its gravity. You've probably heard this before, but it's worth thinking about what it actually means. The moon's gravity pulls on everything on Earth, the rocks, the air, you, me, everything. But water, being fluid, responds to this pull more obviously than solid ground. As the moon orbits Earth, its gravitational pull creates a bulge in the oceans on the side facing the moon. And interestingly, there's also a bulge on the opposite side, because Earth itself is being pulled toward the moon, slightly more than the water on the far side. These bulges travel around the planet as the moon orbits, creating the daily rhythm of high and low tides. Twice a day, the oceans rise. Twice a day, they fall. It's been happening for as long as there's been liquid water on Earth. The sun also creates tides, but they're weaker, only about half as strong as the moon's. When the sun and moon align during new moons and full moons, their tidal forces combine to create especially high spring tides. When they're at right angles, their effects partially cancel out, creating weaker, neap tides. Without the moon, Earth would still have tides from the sun, but they'd be much smaller, only about a third as strong. The dramatic tidal ranges that shape our coastlines, that create tidal pools where early life might have gained a foothold, that influence ocean circulation. All of that exists because of the moon. The ocean remembers the moon twice a day, rising to meet it, then falling away. It's been a conversation between Earth and moon for billions of years. The moon doesn't just create tides in the oceans, it also creates tides in Earth's solid crust and even in the atmosphere, though we don't notice them. The ground beneath you rises and falls by several inches twice a day. Not dramatically, you can't feel it happening, but measurably. If you had sensitive enough instruments, you could detect the solid Earth gently flexing in response to the moon's gravitational pull. These Earth tides are small because rock doesn't flow like water. But rock isn't perfectly rigid either. Over large scales, under enough stress, even solid ground can deform. The moon pulls, and the planet responds, swelling slightly toward and away from it. The atmosphere experiences tides too. The moon's gravity affects the air pressure, creating subtle variations that meteorologists can measure. These atmospheric tides are tiny compared to weather systems, but they exist, a gentle cosmic influence on the blanket of air surrounding our world. It's humbling, isn't it? We think of ourselves as standing on solid ground beneath a stable sky, but really we're on a planet that's constantly flexing, breathing, responding to the moon's presence. Everything is in motion, even the things that seem most permanent. The moon doesn't just light the night, it shapes the world, subtly but continuously, pulling on everything, influencing everything, making its presence felt in ways both obvious and hidden. The moon is slowing Earth's rotation very gradually through something called tidal friction. Here's how it works. As the moon pulls on Earth's oceans, creating those tidal bulges, the Earth is also rotating beneath them. The planet spins faster than the moon orbits, so the tidal bulges get dragged slightly ahead of the moon's position. This creates a kind of gravitational friction, a drag on Earth's rotation. The result? Our days are getting longer, not by much, only about 1.7 milliseconds per century. You won't notice it in your lifetime or in 100 lifetimes. But over geological time, the effect is substantial. Hundreds of millions of years ago, when dinosaurs walked the Earth, a day was only about 23 hours long. Go back further, to the time when the moon first formed, and Earth might have been spinning so fast that a day lasted only 5 or 6 hours. We can see evidence of this in the fossil record. Ancient corals and shellfish grew in layers, like tree rings, and those layers record the number of days in a year. The farther back you go, the more days there were in a year, because each day was shorter. The moon is stealing Earth's rotational energy, slowing us down, making our days longer. And as it does this, that energy has to go somewhere. It goes into the moon's orbit, pushing the moon farther away. That's why the moon is receding at 1.5 inches per year. Energy is conserved. Nothing is lost. It just transforms, shifts from one form to another, from Earth's spin to the moon's orbital distance. A slow cosmic exchange that's been happening for billions of years. The moon stabilizes Earth's axial tilt, and this might be one of the most important things it does for us. Earth's axis is tilted about 23.5 degrees relative to its orbital plane around the Sun. This tilt is why we have seasons. As Earth orbits, different hemispheres lean toward or away from the Sun. But that tilt isn't fixed. It wobbles slightly over thousands of years in a motion called precession. Without the moon, Earth's tilt would vary much more dramatically. Computer simulations show that a moonless Earth could wobble chaotically, with its tilt swinging from almost 0 degrees to 85 degrees over millions of years. Imagine what that would mean for climate. With low tilt, there would be almost no seasons. The equator would bake while the poles froze even more than they do now. With extreme tilt, the poles would point nearly toward the sun at certain times of year, creating unimaginable seasonal extremes. The climate would be unstable, unpredictable, violent. The moon's gravitational presence acts like a gyroscope, keeping Earth's tilt relatively stable. Not perfectly, we still have those small wobbles, but within a narrow range. This stability has given Earth consistent, predictable seasons for hundreds of millions of years. That consistency might have been crucial for the evolution of complex life. Life adapts, yes, but it adapts better to gradual changes than to chaotic lurches. The moon gave Earth the gift of climatic stability, and in that stability, life flourished. We owe more to the moon than we usually realize. It's not just a light in the sky, it's a stabilizing force, keeping our world on an even keel. A full lunar cycle, from new moon to new moon, takes 29.5 days. This is called a synodic month, and it's the rhythm that's governed human timekeeping for millennia. It's not quite the same as the moon's orbital period around Earth, which is 27.3 days. The difference exists because Earth is also moving around the sun. By the time the moon completes one orbit of Earth, our planet has moved along in its own orbit, so the moon has to travel a bit farther to get back to the same phase relative to the sun. But 29.5 days is close enough to being a month that almost every culture in human history has used lunar cycles to track time. Before we had precise mechanical clocks and standardized calendars, the moon was the obvious choice for marking the passage of time. You could look up and see where you were in the month. Many ancient calendars were purely lunar, 12 months of 29 or 30 days each. The Islamic calendar still works this way. Other cultures, like the ancient Hebrews and Chinese, developed lunisolar calendars that tried to keep both the moon phases and the solar year synchronized. Our modern calendar is solar, divorced from the moon's cycles, but the connection remains in our language. The word month comes from moon. When we say once in a blue moon, we're acknowledging the occasional mismatch between lunar cycles and calendar months. The moon taught us to count time. Before we measured hours and minutes, we measured moons. The moon orbits Earth at about 2,288 miles per hour. That's fast. Faster than the speed of sound. Faster than a bullet. And yet, when you watch the moon cross the sky, it seems to move so slowly. It takes hours to go from horizon to horizon. You can look at it, look away, come back later, and it's barely shifted. This is partly an illusion of distance. The moon is so far away that even its tremendous speed looks gentle from our perspective. It's like watching an airplane at high altitude. You know it's traveling hundreds of miles per hour, but it seems to drift lazily across the sky. But it's also real. The moon's orbital speed is matched to its distance and Earth's gravity in a delicate balance. It's moving exactly as fast as it needs to avoid falling to Earth or flying away into space. Any slower, and gravity would pull it down. Any faster, and it would escape. This balance isn't perfect. The moon is slowly spiraling outward, after all. But it's stable enough to have lasted for billions of years. The moon has been circling Earth at roughly this speed for longer than life has existed. There's something peaceful about that thought. Despite the violence of its birth, despite the chaos of the early solar system, the moon found a stable orbit, and has been sailing along that path ever since, constant and reliable. The moon's orbit isn't a perfect circle. It's an ellipse, which means the moon's distance from Earth varies throughout the month. At its closest approach, called perigee, the moon comes within about 225,623 miles. At its farthest point, called apogee, it's about 252,088 miles away. That's a difference of more than 26,000 miles, substantial when you think about it. This elliptical orbit creates some interesting effects. When the moon is at perigee, it moves slightly faster, in accordance with Kepler's laws of orbital motion. Objects move faster when they're closer to what they're orbiting. When it's at apogee, it slows down a bit. The ellipse also means the moon's apparent size in the sky changes. At perigee, the moon looks noticeably larger than at apogee, about 14% bigger in diameter, which translates to about 30% more surface area. If a full moon happens to occur when the moon is at or near perigee, you get what the media often calls a supermoon, a full moon that's slightly larger and brighter than average. It's not a dramatic difference. You probably wouldn't notice unless you were comparing photographs. But it's real. The moon doesn't just circle Earth in a perfect loop. It breathes in and out, drawing closer and pulling away, tracing an ellipse through space, dancing to the mathematics of gravity. When the moon is at perigee, appearing at its largest, it looks about 14% bigger in diameter than when it's at apogee. The media has taken to calling these supermoons, though astronomers sometimes roll their eyes at the term. 14% doesn't sound like much, and honestly, it's not. If you saw the moon at apogee one night and at perigee the next, you'd be hard-pressed to tell the difference without measuring equipment. Our brains aren't calibrated to detect such subtle size changes, especially for an object we're not holding or standing next to. But it does mean a supermoon is technically brighter. About 30% more light reaches Earth because area scales with the square of diameter. That extra light still won't make night into day or cast sharp shadows. The moon is just a bit more luminous, a bit more present. There's something endearing about humanity's fascination with supermoons. We get excited about these small variations, celebrate them, go outside to look at the moon with fresh attention. Maybe the size difference is subtle, but our response to it isn't. It reminds us to look up, to notice, to appreciate what's been there all along. The moon doesn't really change, but our awareness of it does, waxing and waning like its phases, sometimes bright and focused, sometimes dim and forgotten. Supermoons are just an excuse to pay attention again. The moon's rotation is synchronized with its orbit. It takes the same amount of time to spin once on its axis as it does to complete one orbit of Earth. Both take about 27.3 days. This is tidal locking, which we mentioned earlier, but it's worth sitting with the implications. From the moon's perspective, Earth hangs nearly motionless in the sky. If you were standing on the near side of the moon, Earth would always be in roughly the same spot, slowly spinning to show you different continents and oceans, but never rising or setting. From the far side, Earth would never be visible at all. You'd see the stars wheel overhead as the moon rotates, and the sun would rise and set over its long day-night cycle. But Earth would remain forever hidden below the horizon. This locking happened because of Earth's gravitational pull on the moon. Early in its history, the moon probably rotated faster, but Earth's gravity created tidal bulges in the moon's body. Yes, the moon had tides too, in its rocky surface. Those bulges created friction that gradually slowed the moon's rotation until it matched the orbital period exactly. Once locked, it stayed locked. It's a stable configuration. Most large moons in the solar system are tidally locked to their planets for the same reason. It's a kind of cosmic embrace. The moon, captured by Earth's gravity, gradually turned to face us and has been gazing back ever since. Even though the moon is tidally locked, we actually see slightly more than half of its surface over time, about 59% in total. This is because of a wobbling motion called libration. Libration happens for several reasons. First, the moon's orbit is elliptical, so it speeds up and slows down as it orbits, but its rotation rate stays constant. This creates a slight back and forth wobbling in longitude. We can peak around the eastern edge, then later around the western edge. Second, the moon's axis isn't perfectly perpendicular to its orbital plane. It's tilted slightly, which lets us peek over the North Pole and under the South Pole at different times. Third, we observe the moon from Earth's surface, not from its center. As Earth rotates and we're carried from one side of the planet to the other, our viewing angle changes slightly. We can see a tiny bit more around the moon's edges. All these effects combine to give us glimpses of territory that's usually hidden. Not the full far side, that remains largely out of view, but enough to see about 9% more than a perfectly locked moon would show. The moon isn't completely mysterious. It reveals a bit more of itself to patient observers, to those who watch carefully over weeks and months, noticing the subtle shifts in perspective. Even in its constancy, there's variation. Even in its locked position, there's movement. There's a famous optical illusion called the moon illusion. The moon appears much larger when it's near the horizon than when it's high overhead in the sky. You've probably noticed this. The moon rising over distant buildings or hills looks enormous, like you could almost reach out and touch it. But when that same moon is at its zenith, high above, it seems smaller, more distant, less impressive. The strange thing? The moon doesn't actually change size. If you measure its angular diameter with instruments, or even just hold up a coin at arm's length to compare, you'll find it's exactly the same size, whether it's on the horizon or overhead. So why does it look bigger? Scientists have been debating this for centuries, and there's still no consensus. One theory suggests it's because we perceive the sky as a flattened dome rather than a perfect hemisphere. The horizon seems farther away than the zenith, so our brain interprets the moon as larger to compensate. Another theory involves comparing the moon to foreground objects like trees and buildings, which creates a size contrast. Whatever the mechanism, the illusion is powerful. Almost everyone experiences it. We know intellectually that the moon isn't changing size, but we can't help seeing it as larger on the horizon. It's a reminder that perception and reality aren't always aligned. What we see is filtered through our brains, interpreted, adjusted, sometimes distorted. The moon just is. We're the ones adding meaning and scale. Total solar eclipses, those rare events when the moon passes directly in front of the sun and blocks it completely, are only possible because of an extraordinary cosmic coincidence. The sun is about 400 times larger in diameter than the moon, but the sun is also about 400 times farther away from Earth. These two ratios almost perfectly cancel out, making the moon and sun appear nearly the same size in our sky. This is not normal. It's pure chance. There's no physical reason it had to be this way. If the moon were slightly smaller or orbited slightly farther away, it wouldn't be able to completely cover the sun. We'd only get partial eclipses, where the moon takes a bite out of the sun but never fully blocks it. If the moon were larger or closer, it would completely cover the sun with room to spare. Total eclipses would be common and would last longer, but we'd never see the sun's corona, that beautiful ghostly halo of plasma that becomes visible only during totality, when the moon's disk almost exactly matches the sun's. We live in a time when perfect total solar eclipses are possible. Not forever. The moon is drifting away, remember. In several 100 million years, there will be no more total eclipses. Future beings, if any exist, will look at our eclipse photographs the way we look at images of things that no longer exist. We're witnessing something temporary, something precious. The moon and sun appearing the same size in the sky, creating moments of perfect alignment. It won't last forever, but for now, it's ours to see. During a lunar eclipse, when Earth passes between the sun and moon and casts its shadow across the lunar surface, the moon doesn't go completely dark. Instead, it turns a deep, coppery red. This red color comes from Earth's atmosphere. Sunlight traveling toward the moon has to pass through the thin ring of Earth's atmosphere, as seen from the moon's perspective. Our atmosphere acts like a filter, scattering away the blue light, the same scattering that makes our daytime sky blue, and bending the red light around Earth's edges toward the moon. So the light illuminating the moon during a lunar eclipse is actually sunlight that has passed through all the sunrises and sunsets happening on Earth at that moment. Every dawn and dusk on the planet, simultaneously, contributing their red and orange glow. Think about that. The moon, sitting in Earth's shadow, is being lit by the accumulated light of every sunrise and sunset on our entire planet, all at once. It's poetic in a way. The moon, even when Earth blocks its light, still receives something from us, a different kind of illumination, softer, redder, filtered through the atmosphere that makes our world livable. Ancient peoples sometimes feared lunar eclipses, seeing the blood-red moon as an omen. But really, it's just Earth giving the moon a different kind of light. A reminder that even in shadow, there's still beauty. The moon has been visited by 12 human beings, all between 1969 and 1972. 12 people, out of the billions who have lived, have walked on another world. Neil Armstrong and Buzz Aldrin were first, during Apollo 11 in July 1969. Then came Apollo 12, 14, 15, 16, and 17. Apollo 13 was supposed to land, but had to abort after an oxygen tank exploded. 12 men walked on the surface, collected rocks, planted flags, took photographs, and came home. And then we stopped. The last human to walk on the moon, Eugene Cernan, left in December 1972. That was over 50 years ago. No human has been back since. No human has even left low Earth orbit since then. It's strange, isn't it? We went to the moon 6 times in 3.5 years, and then never again. The momentum stopped. The political will evaporated. The funding dried up. And the moon, which had been briefly touched by human presence, returned to its solitude. Those 12 astronauts are all getting old now. Several have passed away. Soon there will be no one left alive who has stood on another world. The experience will pass from living memory into history, something we read about rather than something we can hear firsthand. But the footprints remain. The equipment remains. The flags, though likely bleached white by solar radiation by now, still stand. We left our mark. Brief, perhaps, but indelible in the moon's unchanging landscape. The moon is the only celestial body beyond Earth that humans have physically touched with their own hands. Every other world we've explored has been through robotic proxies. Rovers, landers, flyby spacecraft sending back data from afar. We've sent robots to Venus, Mars, Jupiter's moons, Saturn's moons, even comets and asteroids. We've explored more of the solar system than ever seemed possible. But only the moon has felt the direct touch of human hands, the boot prints of human feet, the physical presence of human bodies. There's something profound about that distinction. Remote exploration is amazing. We can learn incredible things through robotic missions. But there's a different quality to sending people. It's not just about gathering data. It's about witness, about experience, about standing in a place and looking around with your own eyes, not through a camera relay. The 12 men who walked on the moon described it with words that robots never could. The smell of the dust, the way the horizon appeared sharper than any horizon on Earth because there's no atmosphere to blur it. The overwhelming sensation of standing in a place no human had ever been, looking back at Earth hanging in the black sky like a fragile blue marble. Robots can measure and analyze. Humans can feel and wonder. Both have their place, but they're not the same. And so far, only the moon has received both. Astronauts who visited the moon reported that lunar dust smells like spent gunpowder, a sharp, acrid, slightly chemical scent. This was unexpected. The moon has no atmosphere, no oxygen, no combustion. Why would it smell like something burning? The answer has to do with how the dust forms and what happens to it. Lunar dust is created by billions of years of meteorite impacts, each one shattering rock into fine particles. But unlike Earth dust, which gets weathered and rounded by water and air, lunar dust particles remain jagged and sharp, like tiny shards of glass. These particles are also constantly bombarded by solar wind, charged particles streaming from the sun. This bombardment creates highly reactive chemical bonds on the dust's surface. When astronauts brought the dust inside their lunar module, where there was air and moisture, those reactive surfaces immediately started interacting with oxygen and water vapor. The smell was likely coming from these chemical reactions. Lunar dust that hadn't been in contact with an atmosphere for billions of years, suddenly encountering oxygen and releasing energy in the process. It's not actually burning, but it's chemically similar. The dust was also a problem. It got everywhere, clung to everything, worked its way into equipment seals and spacesuits. It's abrasive and potentially harmful to breathe. Future lunar missions will need to figure out how to deal with it. But that smell, that unexpected gunpowder smell, was a reminder that the moon is alien. Even its dust behaves in ways we don't encounter on Earth. Moon dust is incredibly abrasive and posed serious problems for the Apollo missions. It's not like Earth dust at all. On Earth, dust particles get rounded and smoothed over time by wind and water. Even desert sand, which feels sharp, has been tumbled and worn. But on the moon, with no atmosphere and no water, the dust remains as sharp as the day it was created by meteorite impacts. Under a microscope, lunar dust particles look like tiny pieces of shattered glass, all angles and sharp edges. And because the moon has no weather to wear them down, they stay that way indefinitely. This caused real problems for the Apollo astronauts. The dust scratched their helmet visors, reducing visibility. It worked its way into the joints of their spacesuits, making movement more difficult. It clung to everything because it's electrostatically charged from solar wind bombardment. They couldn't brush it off easily. Worse, it's potentially dangerous to human health. Some astronauts experienced respiratory irritation after breathing small amounts of it inside their lunar modules. The particles are so fine and sharp that they could damage lung tissue if inhaled regularly. For future long-term lunar missions, dealing with the dust is one of the biggest challenges. You can't just shake it off. You need airlocks, special cleaning procedures, dust-proof seals on equipment. The moon's dust is a reminder that even something as simple as dirt can be a hazard in an alien environment. The moon has practically no erosion. On Earth, wind and water and ice constantly wear away at surfaces, smoothing them, changing them, erasing the past. Mountains crumble, coastlines shift. Even the hardest rock eventually weathers away. Not on the moon. Without air or water, the only erosion comes from occasional meteorite impacts and the slow effects of solar radiation. A crater formed 1 billion years ago looks almost the same today as when it was fresh. The edges haven't worn down. The debris hasn't been washed away. It's frozen in time. This makes the moon's surface an archive, a record of impacts stretching back billions of years. Every scar tells a story. The heavily cratered highlands preserve information about the early solar system, when impacts were far more common. The smoother maria show what happened later, after volcanic activity covered the oldest craters. Geologists love this about the moon. On Earth, most of the geological record has been erased, recycled through plate tectonics, worn away by weather. The oldest rocks on Earth are only about 4 billion years old, and they're rare. But on the moon, ancient rocks are everywhere, just sitting on the surface waiting to be studied. Every impact crater is a time capsule. Every rock is a survivor. The moon remembers everything because it has no mechanism for forgetting. Its surface is a museum of the solar system's violent past, preserved in perfect detail. The oldest rocks brought back from the moon are about 4.5 billion years old, roughly the same age as the solar system itself. These rocks are called anorthosites, and they're part of the moon's original crust, formed when the entire lunar surface was covered by an ocean of molten rock. As this magma ocean cooled, less dense minerals floated to the top and solidified, creating the light-colored highlands we see today. On Earth, finding rocks this old is nearly impossible. Earth's surface is constantly recycled through plate tectonics. Continents move, subduct, melt, and reform. Mountains rise and erode. The planet has been geologically active for its entire existence, which means the oldest rocks have mostly been destroyed or buried. The oldest Earth rocks we've found are about 4.4 billion years old, and they're tiny zircon crystals, not entire formations. The moon, by contrast, has vast expanses of 4.5 billion-year-old crust just sitting on the surface. Studying these ancient lunar rocks tells us about the conditions in the early solar system, how hot things were, how planets formed, what materials were available. They're witnesses to events that happened before Earth had oceans, before life existed, before most of what we think of as Earth's history even began. Holding a lunar rock is like holding a piece of deep time, touching something that's barely changed since the solar system was young. It's as close as we can come to visiting the distant past. Earth rocks have been found on the moon, blasted there by ancient asteroid impacts. This sounds impossible at first. How could a rock from Earth end up on the moon? But when you think about the violence of large asteroid impacts, it starts to make sense. When a really big asteroid hits Earth, we're talking something miles across, traveling at tens of thousands of miles per hour. The energy released is staggering. The impact excavates enormous amounts of material and throws it upward at tremendous speeds. Most of this debris falls back to Earth, but some of it is traveling so fast that it escapes Earth's gravity entirely. Some of that material eventually hits the moon. It's been happening throughout the history of the Earth-Moon system. Earth rocks, carrying information about our planet's ancient surface, end up on the moon where they're preserved in that airless, erosion-free environment. Scientists have identified a few rocks collected during Apollo missions that appear to have originated on Earth. They have chemical signatures and minerals that match Earth's composition better than the moon's. This is exciting because it means the moon might hold fossils of Earth's early history. Rocks from a time before plate tectonics recycled everything, maybe even rocks from when life first emerged. They're out there on the moon's surface, mixed in with lunar rocks waiting to be found. The moon isn't just a separate world, it's also an archive of Earth's past, holding pieces of our planet's history that might be lost here at home. The moon has mysterious, bright patterns on its surface called swirls, snake-like, sinuous features that are brighter than their surroundings and seem to have no obvious origin. These swirls don't correlate with topography. They're not raised or depressed, they're just brighter, as if something protected those areas from the darkening that affects the rest of the surface over time. They're associated with small-scale magnetic fields, little pockets where the lunar surface still has some residual magnetism, even though the moon's global magnetic field died billions of years ago. Scientists think these magnetic fields might deflect the solar wind, protecting the surface beneath from the darkening effects of constant particle bombardment. But how these magnetic anomalies formed in the first place is a mystery, and why they create these specific swirling patterns is also unclear. They're not random. They have structure, flow, almost an aesthetic quality to them. Some look like brushstrokes painted across the lunar surface. The largest and most famous is called Reiner Gamma, and it's visible even from Earth through a good telescope. It looks like someone took a giant brush and painted bright flowing designs across the dark Maria. The moon has its art, its patterns that we don't fully understand. Nature creating forms that seem almost intentional, almost designed, but actually emerging from processes we're still working to decode. Some regions on the moon have weak mini-magnetospheres, small-scale magnetic fields that deflect solar wind particles, creating protective bubbles above the surface. These aren't like Earth's global magnetic field. They're tiny, localized, scattered around the moon without much pattern. But within their small domains, they actually provide some protection from radiation. This is potentially important for future lunar exploration. Radiation is one of the biggest hazards astronauts face on the moon. Without an atmosphere or magnetic field, cosmic rays and solar particles hit the surface directly. Long-term exposure could cause serious health problems. But if there are locations where natural magnetic fields provide some protection, even if it's partial, those might be ideal sites for lunar bases. You'd get some shielding for free, reducing the amount of artificial protection you'd need to build. Scientists are still mapping these magnetic anomalies, trying to understand their distribution and strength. Some are stronger than others. Some cover larger areas. Future missions might specifically target these locations for this very reason. The moon's ancient magnetic field is gone, but these remnants remain, scattered pockets of protection, like memories of a time when the moon had its own shield. And those memories might be useful, might help protect the next humans who visit. It's interesting how the past can serve the future, how something long dead can still provide shelter. The moon rings like a bell when struck by meteorites or spacecraft. This was one of the most surprising discoveries from the Apollo missions. The astronauts left seismometers on the lunar surface, and when they deliberately crashed parts of their spacecraft into the moon to create measurable impacts, something strange happened. The moon didn't just shake briefly and stop. It reverberated for hours, sometimes for more than 3 hours after a single impact. On Earth, seismic waves from earthquakes die away relatively quickly because our planet's interior is somewhat soft and layered. The waves get absorbed, dampened, scattered by all the different materials and structures inside. But the moon's interior appears to be much more rigid and uniform. When it's struck, the vibrations just keep bouncing around inside, reflecting off boundaries, continuing long after the initial impact. Scientists sometimes described it as the moon ringing like a bell, though that's perhaps too musical a description. It's more like a deep, subsonic hum that slowly fades over hours rather than seconds. This tells us something about the moon's internal structure. It's cold inside, solid, the kind of structure that doesn't absorb energy easily. The moon remembers being struck, holds on to the vibration, lets it echo through its body before finally releasing it. Even the moon's seismic behavior speaks to its nature as a world that preserves, that holds onto things, that doesn't let go easily. The moon has an extremely thin exosphere, barely qualifying as an atmosphere at all, made of argon, helium, neon, and sodium atoms. The density is so low that these atoms almost never collide with each other. On Earth, air molecules are constantly bouncing off each other, creating pressure and carrying sound. But on the moon, the atoms are so sparse that each one is essentially alone, following its own trajectory, more likely to hit the surface than another atom. This exosphere doesn't provide any protection from radiation or meteorites. It doesn't create weather or carry sound. It's just a handful of atoms bouncing around above the surface, constantly being replenished by the solar wind and by atoms escaping from the lunar surface itself. Some of these atoms come from radioactive decay in lunar rocks. Argon, for instance, is produced when potassium decays naturally over millions of years. It seeps out of the rocks and escapes into space, but there's always a tiny amount present around the moon at any given time. It's not enough to breathe, not enough to create any kind of atmospheric effect, but it's not nothing either. The moon isn't completely airless, it just has the faintest whisper of an atmosphere, so thin that calling it an atmosphere feels generous. Even in its near vacuum, the moon has this ghostly presence of atoms, coming and going, present but barely, a reminder that nothing in the universe is ever truly empty. Sodium atoms escaping from the moon create a faint tail, extending hundreds of thousands of miles into space, invisible to the naked eye but detectable with specialized instruments. This tail is created by solar radiation pressure. Sodium atoms on the moon's surface get knocked free by solar wind and ultraviolet light. Once free, these atoms are pushed away from the sun by the pressure of sunlight itself. Light has momentum, tiny as it is, and over time it can push individual atoms across vast distances. The result is a thin stream of sodium atoms flowing away from the moon in the direction opposite to the sun, like a comet's tail, but far more tenuous. It stretches for hundreds of thousands of miles, waving gently in the solar wind. You could never see it with your eyes. Even with a telescope, it's invisible. But instruments that can detect sodium's characteristic yellow spectral line can map it out, trace its shape, watch how it changes as the moon orbits. It's strange to think about. The moon, which seems so solid and permanent, is constantly losing atoms to space. They drift away, one by one, carried on light itself, creating this ghostly trail that extends far beyond the moon's surface. Nothing is truly static. Even the moon is slowly bleeding into space, atom by atom, creating patterns in the void that we've only recently learned to see. The moon glows in the dark, very faintly, due to chemical reactions on its surface. Even when completely shadowed during a lunar eclipse, the moon isn't totally dark. It chemiluminesces. This glow is incredibly faint, far too dim for human eyes to detect, but sensitive instruments can measure it. The glow comes from the lunar surface being constantly bombarded by cosmic rays and solar wind particles, which create excited chemical states in the regolith. When these excited states decay back to their normal state, they release tiny amounts of light. It's not much. Nothing like the reflected sunlight that normally illuminates the moon. But it's there, a faint intrinsic glow, the moon producing its own light through the relentless bombardment of space radiation. In a way, the moon is always experiencing impacts. Not just the dramatic collisions of asteroids that create craters, but the constant, invisible rain of particles from the sun and beyond. Each particle delivers a tiny amount of energy. Collectively, they're enough to make the moon glow, however faintly. Even in complete darkness, the moon has its own light. Not borrowed from the sun, but generated by its interaction with the environment of space. It's a cold light, a chemical light, but light nonetheless. The moon isn't just a reflector. It's an active participant in its cosmic environment, responding to radiation by glowing back, faintly but persistently. Apollo astronauts observed a phenomenon called horizon glow just before sunrise on the moon, a faint luminescence appearing above the horizon before the sun itself rose. The glow looked like a thin, bright line hovering just above the lunar surface. It was unexpected and somewhat mysterious. What could be glowing before the sun came up, when there should be nothing but darkness and vacuum? The leading explanation involves electrically charged lunar dust. The intense ultraviolet radiation from the sun ionizes dust particles on the surface, giving them an electric charge. Like charges repel, so these charged particles might actually levitate slightly, rising a few feet or even tens of feet above the surface. When the sun is just below the horizon, Its light could catch these levitating dust particles before illuminating the surface itself, creating that horizon glow the astronauts saw. It's still somewhat speculative. We don't have definitive proof this is what's happening, but it fits with what we know about the moon's electrical environment. The surface is constantly being charged by solar wind and UV radiation. Dust is abundant and fine-grained. It's plausible that some of it levitates. If true, it means the moon has a very thin, constantly changing layer of floating dust. Invisible most of the time, but revealed at sunrise and sunset when the light hits it just right. Even the dust on the moon isn't entirely stationary. It trembles, levitates, responds to electrical forces in ways we're only beginning to understand. The moon experiences more meteorite impacts than Earth because it has no atmosphere to burn up incoming objects. On average, about 2,800 pounds of meteorites strike the moon every day. That's more than a ton of space rock, every single day, raining down on the surface. Most of these are small, pebbles, dust, tiny fragments, but some are larger. And without an atmosphere to slow them down or break them apart, they hit the surface at full cosmic velocity, tens of thousands of miles per hour. Each impact, no matter how small, adds to the moon's cratered surface. Each one creates a tiny new crater or contributes to the gradual pulverization of surface rock into regolith. Over billions of years, this constant bombardment has churned the upper layers of the moon's surface, mixing materials, breaking down rocks, creating that deep layer of fine dust. Earth gets hit by meteorites too, of course, but our atmosphere is a shield. Most small objects burn up completely before reaching the ground. We see them as shooting stars, brief, beautiful, harmless. Only the very largest make it through, and even they're slowed and often broken apart. The moon has no such protection. Every rock, every fragment, every dust grain from space that crosses its path slams into the surface at full speed. The moon bears the scars that Earth's atmosphere prevents us from receiving. In a way, the moon takes hits for us, standing between Earth and some of the debris that would otherwise reach our planet. An unintentional shield, absorbing impacts in silence. The moon's mass is about 1.2% of Earth's mass. This might not sound like much, but it's actually quite unusual for a planet-moon system. Most planets have moons that are tiny compared to themselves. Jupiter is vastly larger than any of its moons. Saturn dwarfs even Titan, its largest satellite. Mars's moons are little more than captured asteroids. Even Neptune's Triton, which is substantial, is still a small fraction of Neptune's mass. But Earth and the moon are different. The moon is large enough relative to Earth that the center of mass of the Earth-Moon system, the point around which both bodies actually orbit, isn't at Earth's center. It's about 1,700 miles below Earth's surface, roughly 3/4 of the way out from the planet's core. This means we're not simply a planet with a moon orbiting around us. We're more like a binary planet system, two worlds orbiting their common center of mass, though one is much larger than the other. Some scientists argue we should think of Earth and Moon as partners rather than as primary and satellite. They're locked in a gravitational dance that affects both bodies profoundly, slowing Earth's rotation, causing the Moon to recede, creating tides that might have been crucial for the development of life. The moon is our companion in a deeper sense than most moons are to their planets. We're bound together in an unusually intimate gravitational relationship that's been shaping both worlds for billions of years. The moon is actually egg-shaped, not perfectly spherical. It's stretched slightly along the Earth-Moon axis due to tidal forces. When the moon was young and its interior was still somewhat molten, Earth's gravity pulled on it, creating bulges toward and away from Earth. As the moon cooled and solidified, these bulges became frozen into its structure. So now the moon is elongated, with its longest axis pointing toward Earth. The difference isn't dramatic. The moon is only about half a mile wider along the Earth-Moon line than it is perpendicular to it. You'd never notice just by looking, but it's measurable and it's permanent. This shape is part of what locked the moon's rotation to its orbit. The tidal bulge created torque that slowed the moon's rotation until it matched the orbital period, keeping the same face and the same bulge pointed toward Earth. It's a shape born from relationship, from the gravitational pull between two bodies. The moon's form is literally molded by its connection to Earth, stretched and held in place by forces that have been acting for billions of years. We shape each other, Earth and moon. We pull on each other, deform each other slightly, change each other's behavior. The relationship is written into the very structure of both worlds. The moon's center of mass doesn't align with its geometric center. It's offset by about a mile. This asymmetry is subtle but significant. Scientists aren't entirely sure why this offset exists. It might have to do with how the moon formed, with the distribution of dense and light materials in its interior, with the way the lunar crust thickened differently on the near and far sides. What's interesting is that this offset might have influenced which face became tidally locked toward Earth. When the moon was rotating freely, before tidal locking, the gravitational interaction with Earth would have been slightly stronger when the denser side was pointed toward us. Over millions of years, this small difference could have created enough torque to gradually orient the moon so that the denser, offset side stayed pointed earthward. It's like a weighted die that tends to settle with certain faces up. The moon had a preferred orientation, and tidal forces pushed it into that orientation and held it there. So the face we see might not be random. It might be the heavier side, the side that was gravitationally favored to point toward Earth. The moon's internal asymmetry determined its eternal posture. Even in something as simple as which side faces which way, there are layers of explanation, subtle causes working over immense timescales to create the configuration we now take for granted. Gravity varies across the moon's surface due to dense concentrations of mass called mascons, short for mass concentrations. These mascons are regions where the moon's subsurface is unusually dense, typically beneath the large impact basins where Maria formed. When asteroids created those giant craters and lava later flooded them, the dense basaltic rock created gravitational anomalies, spots where gravity is slightly stronger than average. Spacecraft orbiting the moon discovered these mascons when their trajectories deviated slightly from predictions. As an orbiter passes over a mascon, the extra gravitational pull speeds it up slightly and alters its path. Careful tracking of these deviations allowed scientists to map out where the mascons are located. This matters for future missions. If you want to orbit the moon for an extended period, you need to account for mascons, or they'll gradually destabilize your orbit. The moon's gravitational field isn't uniform. so maintaining a stable orbit requires more attention and fuel than it would around a perfectly smooth, homogeneous body. Even the moon's gravity has texture, has variation, has these lumps and valleys in its gravitational field corresponding to the distribution of mass below the surface. Gravity, which we think of as smooth and predictable, is actually bumpy and complex when you look closely enough. The moon holds its secrets even in invisible things like gravitational fields, revealing them only through careful measurement and patience. The moon has a tiny core, making up only about 1 to 2% of its total mass. Compare that to Earth, where the core comprises roughly 32% of our planet's mass. This small core is part of what makes the moon so different from Earth. A large, hot core creates convection currents, the motion of liquid metal that generates a magnetic field. It provides heat that drives geological activity. It influences how the planet evolves over billions of years. The moon's core is small, probably only about 150 to 250 miles in radius, and it cooled relatively quickly after the moon formed. Without a substantial core, the moon couldn't maintain a strong magnetic field for long. Without ongoing heat from the core, volcanic activity eventually ceased. The moon became geologically quiet much faster than Earth did. There's something almost sad about it, if you allow yourself to anthropomorphize a celestial body. The moon had a brief period of activity. Volcanism, a magnetic field, moonquakes, geological change, and then it went dormant. Its small size meant it couldn't hold on to its internal heat long enough to sustain those processes. Earth is still geologically active billions of years later, because it's large enough to retain heat, because its core is substantial and still churning. The moon, smaller and with a tiny core, settled into geological silence relatively early. Size matters in the life of a world. The moon's small core determined much of its fate. A brief geological youth followed by eons of stillness. The moon's core may still be partially molten, though this remains uncertain. Scientists have been trying to figure out the exact state of the moon's interior for decades. Seismic data from the Apollo missions gave us some information, but it wasn't detailed enough to definitively answer whether the core is completely solid or still has a liquid portion. More recent studies, using careful measurements of how the moon wobbles in its orbit and how it responds to Earth's gravitational pull, suggest there might be a small molten region at the very center. If there is liquid metal in the moon's core, it's probably just the innermost part, maybe 150 miles in radius or less, surrounded by a solid layer. Not enough to generate a magnetic field through dynamo action, but enough to affect how seismic waves travel through the moon and how it deforms in response to tidal forces. It's a subtle question, but it matters. The state of the core tells us about the moon's thermal history, about how fast it cooled, about what its interior composition might be. A partially molten core would mean the moon still has some residual heat from its formation, still holds onto a tiny fraction of the energy it had billions of years ago. Even in its quietness, the moon might not be completely cold. There might be a small, warm heart deep inside, hidden beneath miles of cold, solid rock, slowly cooling but not yet entirely frozen. The moon keeps this secret well. We can only infer what's inside from subtle measurements and careful analysis. The moon has caves and lava tubes that could shelter future lunar habitats. These aren't just theoretical. We've found evidence for them. Lava tubes form when molten lava flows beneath a hardened crust. The surface solidifies while liquid rock continues to flow underneath, eventually draining away and leaving a hollow tunnel. On Earth, lava tubes can be large enough to walk through, sometimes even drive through. On the Moon, with its lower gravity and apparently more fluid ancient lava, these tubes might be enormous. Some estimates suggest lunar lava tubes could be hundreds of feet wide and extend for many miles underground. Recent observations have found collapsed sections of these tubes, places where the roof fell in, creating a pit or skylight that opens into the tunnel below. These pits are visible in high-resolution images from lunar orbiters. They're dark, circular openings in the surface, leading down into unknown depths. For future astronauts, these lava tubes would be ideal shelters. Underground, you're protected from radiation, from meteorite impacts, from the extreme temperature swings on the surface. The rock overhead acts as natural shielding, far better than anything we could build easily. Imagine a lunar base built inside a lava tube, a city underground with stable temperatures, radiation protection, and ample space. The tube becomes your ready-made structure. You just need to seal it and pressurize it. The Moon, in its ancient volcanic past, might have inadvertently built shelters for its future visitors. Some lunar lava tubes might be large enough to contain entire cities. Not small outposts, but actual cities with multiple buildings, streets, and thousands of inhabitants. On Earth, the largest lava tubes are maybe 30 or 40 feet in diameter. Impressive, but not city-sized. But the Moon's gravity is only 1/6 of Earth's, which means the roof of a lava tube can span much wider before it becomes unstable and collapses under its own weight. Scientists have calculated that stable lunar lava tubes could be as wide as 3,000 feet, more than half a mile in diameter. They could extend for tens or even hundreds of miles, creating vast underground networks. A tube that large could house an entire human settlement. You could build multiple levels inside, creating a three-dimensional city in the protected environment underground. Natural temperature stability, radiation shielding from meters of rock overhead, protection from micrometeorites, and the harsh surface environment. We're talking about natural structures that dwarf anything humans have built underground on Earth. The Moon, through its ancient volcanism, might have created ready-made habitats far superior to anything we could construct on the surface. Finding and exploring these tubes will be a priority for future missions. They represent not just scientific curiosities, but potential homes, places where humans could live for extended periods, perhaps permanently, protected by the Moon's own stone. The Moon, which seems so barren and hostile on the surface, might be far more welcoming just below, in these hidden chambers it created billions of years ago. The Moon has lunar swirls that are less space-weathered than surrounding terrain, bright patches that somehow resist the darkening that affects everything else. Normally, the Moon's surface gradually darkens over time due to space, weathering. Solar wind particles and micrometeorite impacts break down the surface minerals, creating tiny glass beads and metallic iron particles that darken the regolith. It's a slow process, but relentless. Except in these swirl regions, somehow these areas remain bright, as if they're protected from space weathering. The correlation with localized magnetic fields suggests that these small-scale magnetic bubbles might deflect the solar wind, preventing it from darkening the surface beneath. But the details are still mysterious. Not all magnetic anomalies have swirls. Not all swirls have clear magnetic associations. And the patterns of the swirls themselves, those flowing, sinuous shapes, don't have an obvious explanation. Some scientists have proposed that the magnetic fields formed when ancient comets hit the moon, vaporizing and creating plasma that temporarily generated strong magnetic fields, which then froze into the lunar crust. Others suggest the fields are remnants of the moon's ancient global field, somehow preserved in certain locations. Whatever the cause, the swirls remain, bright mysteries painted across the lunar surface, patterns that seem almost intentional, almost artistic, but are really just the result of processes we don't yet fully understand. The moon creates art through physics. The swirls are beautiful not because they were designed to be, but because natural forces, acting blindly, happen to create forms that please the human eye. The moon has a mountain nearly as tall as Mount Everest. It's called Mons Huygens, and it rises about 18,000 feet above the surrounding plain. Mount Everest, Earth's tallest mountain, rises 29,000 feet above sea level. So Mons Huygens is roughly 60% as tall, which is substantial. But remember, the moon is much smaller than Earth. Its diameter is only about 1/4 of Earth's. Relative to the size of the world it's on, Mons Huygens is actually quite impressive. This mountain is part of the Montes Apenninus range, which forms part of the rim of the Mare Imbrium impact basin. It's not a volcanic peak like many mountains on Earth. It's impact-related, part of the raised rim created when a massive asteroid struck the moon billions of years ago. Standing on the moon's surface at the base of Mons Huygens, looking up, the mountain would loom above you just as dramatically as any mountain on Earth. Maybe more so, because the lack of atmosphere means the peak would appear razor-sharp against the black sky, with no haze or atmospheric distortion to soften it. And if you wanted to climb it, you'd have an advantage. In the moon's low gravity, each step would take you higher, and you'd weigh only 1/6 what you do on Earth. The climb would still be challenging. You'd need a spacesuit, and the terrain is rough, but it would be a different experience than climbing any mountain on Earth. The moon has its own geography, its own dramatic landscapes, just as worthy of exploration and wonder as anything on our home planet. The moon has no plate tectonics, which means its surface preserves ancient history better than Earth's. On our planet, the surface is constantly being recycled. Earth's crust is broken into plates that move, collide, subduct beneath each other, and resurface as new crust at mid-ocean ridges. This process, driven by heat from Earth's interior, means the ocean floor is relatively young. Most of it is less than 200 million years old. Old crust gets pushed down into the mantle, melts, and gets recycled. Continental crust lasts longer, but even it gets worn down by erosion, folded by tectonic forces, altered by heat and pressure. Very little of Earth's original surface remains. The moon doesn't have any of this. No plate tectonics, no recycling of the crust. The surface that formed billions of years ago is still there, modified only by impacts and the slow effects of space weathering. This makes the moon a frozen archive. Every impact basin, every ancient lava flow, every feature older than a few billion years has been preserved. The moon's surface is like a history book whose pages haven't been torn out or overwritten. If you want to understand what the early solar system was like, you look at the moon. If you want to know what Earth might have looked like 4 billion years ago, the moon offers clues. It's a museum of ancient surfaces, a record of a time when planets were still forming and being bombarded by the debris left over from their creation. The moon remembers because it has no mechanism for forgetting. Its surface is memory made stone. Some lunar Maria formed over 1 billion years after the moon itself formed. Volcanic activity on the moon continued much longer than scientists initially expected. When the Apollo missions first brought back dated samples, it became clear that different Maria had different ages. Some formed around 3.8 billion years ago, others as recently as 3 billion years ago. That's a span of 800 million years of volcanic activity, and some recent research suggests some lava flows might be even younger, possibly only 100 million years old. For a body as small as the moon, this is surprising. Small bodies cool quickly. They lose their internal heat and become geologically dead relatively fast. Scientists expected the moon to have gone quiet shortly after formation. But the Maria tell a different story. They show that the moon had enough residual heat, or perhaps enough heat from radioactive decay, to partially melt its interior and produce lava for hundreds of millions of years, possibly over 1 billion years. This extended volcanic history means the moon was more geologically active than its size would suggest. It wasn't a brief flare of activity followed by immediate dormancy. It was a slow decline, a gradual cooling, with volcanic episodes continuing intermittently for an immense span of time. The youngest Maria might have flowed when life on Earth was already complex and multicellular. The moon was still reshaping its surface while Earth was developing the biosphere that would eventually produce us. Even in its slow death, the moon took its time, holding on to its heat, producing lava long after it should have gone cold. The moon's far side has a much thicker crust than the near side. This is one of the moon's most puzzling asymmetries. The near side crust is roughly 30 miles thick on average. The far side crust is about 50 miles thick. That's a huge difference, and it has visible consequences. Almost all of the dark Maria, those lava-flooded impact basins, are on the near side. The far side has very few. Why? Because when asteroids created large impact basins on the far side, the crust there was too thick for the impact to crack through to the mantle. Lava couldn't reach the surface easily. On the near side, with its thinner crust, impacts could break through, allowing magma to well up and flood the basins. But why is the crust thicker on the far side in the first place? That's the mystery. The moon formed from debris that should have been relatively uniform. Why would one hemisphere develop a thicker crust? One theory suggests it has to do with tidal heating from Earth. The near side, always facing Earth, might have stayed slightly warmer, preventing the crust from thickening as much. Another theory proposes that heat-producing radioactive elements somehow concentrated on the near side, keeping the crust thinner there. We don't have a definitive answer. The moon's asymmetry is real, dramatic, and visible, but its cause remains one of those open questions that future missions might help resolve. The moon is lopsided, uneven, asymmetric in ways we don't fully understand. Even in something as fundamental as its structure, it holds mysteries. The moon helped life evolve on Earth by creating stable tidal pools, rhythmic habitats that may have been crucial environments for early life. Tides create a unique ecological niche. As the tide comes in, pools fill with seawater, bringing nutrients, minerals, and organic molecules. As the tide goes out, pools become isolated, concentrating those materials, creating environments where chemical reactions can occur in relative isolation before the next tide arrives. This daily rhythm might have been important for the origin of life. Some scientists think tidal pools could have been the crucibles, where simple organic molecules assembled into more complex structures, eventually leading to self-replicating molecules, and ultimately, life. The moon's tidal forces also kept Earth's oceans mixed and circulating, preventing stagnation. Ocean circulation distributes heat, nutrients, and dissolved gases, all important for life. Without tides, the oceans might have been less dynamic, less hospitable. Moreover, tides affect coastal erosion, creating diverse coastal environments, marshes, estuaries, intertidal zones. These are rich ecosystems today and might have been important habitats for early life, transitioning from water to land. The moon didn't create life, obviously, but it might have created the conditions that made life's emergence more likely, or faster, or more successful. It shaped Earth's environment in ways that were conducive to biology. We're here in part because the moon was there, pulling on our oceans, creating rhythms and opportunities that might have been crucial for life's beginnings. Ancient corals and shells show that the moon was much closer to Earth billions of years ago. These fossils preserve a record of ancient tides written in layers of growth. Corals and some shellfish grow in daily and monthly rhythms, laying down new material in response to tidal cycles and day-night patterns. These growth patterns create visible bands, like tree rings. By counting them, scientists can determine how many days were in a month, how many hours were in a day, at the time that organism was alive. Fossils from 900 million years ago show that Earth's day was only about 18 hours long back then. Go back even further, and days were even shorter. Calculations based on these fossil records suggest that when the moon first formed, it might have been only 15,000 to 20,000 miles away from Earth, about 1/10 its current distance. Imagine that. The moon hanging in the sky 10 times larger than it appears today, dominating the heavens, creating tides hundreds of feet high, pulling on Earth with tremendous force. Over billions of years, as the moon stole Earth's rotational energy and converted it into orbital distance, the moon slowly receded. The tides became smaller. Days became longer. The moon shrank in the sky, gradually becoming the familiar size we see now. But the record remains, written in stone, preserved in the growth bands of ancient organisms that lived and died under a moon much closer and more dominant than the one we know. The moon's history is written not just on its own surface, but in Earth's fossils. Life itself has recorded the moon's slow departure. The moon keeps one hemisphere perpetually facing away from Earth, and from that far side, Earth never rises. It never appears above the horizon. It's simply absent. Try to imagine being on the moon's far side. You'd see the stars wheeling overhead as the moon rotates. You'd see the sun rise and set over the course of the long lunar day. You'd see the same constellations humans have watched for millennia, though they'd never move across the sky the way they do from Earth's surface. But Earth, that blue marble that astronauts on the near side describe with such awe would be nowhere. Not setting, not rising, just not there. The only home humanity has ever known would be hidden behind thousands of miles of rock, forever out of sight. This makes the far side one of the most isolated places accessible to humans. Even in space, even on the moon's near side, you can look up and see Earth, that connection to home. But on the far side, you're cut off. Radio signals can't reach you directly. They have to be relayed by satellites. Future astronauts exploring the far side will experience a kind of isolation no human has yet felt. Not just far from Earth in terms of distance, but visually, psychologically cut off from it, unable to see it, unable to communicate directly, truly alone in a way that's different from any other kind of solitude. The far side isn't just geographically different, it's existentially different, a place where Earth doesn't exist in your sky. The moon's surface is covered in a layer of fine powder and rubble called regolith, material that ranges from dust-fine particles to boulder-sized chunks, all mixed together. Regolith isn't soil. Soil on Earth is full of organic matter, living organisms, weathered minerals. Lunar regolith is purely mineral, pulverized rock, glass beads from impacts, fragments of every size, all mixed into a loose, gray blanket covering the solid rock beneath. This layer has been accumulating for billions of years. Every meteorite impact, large or small, breaks down surface rock and contributes to the regolith. The layer is constantly being churned by ongoing impacts, mixing older material with newer, creating a complex, layered deposit. Walking on it, astronauts found it had an odd consistency. Fine like powder on top, but it compacts under pressure. Their boots sank in slightly, leaving clear footprints. It clung to everything with static electricity, worked its way into seals and joints, was generally a nuisance despite its fine texture. The regolith holds information about the moon's bombardment history. By studying its composition and structure at different depths, scientists can reconstruct when different impacts occurred, what kinds of objects hit the moon, how the impact rate changed over time. It's an archive written in dust. Every grain has a story, where it came from, what impact created it, how long it's been sitting on the surface. The regolith remembers the moon's entire history of being pummeled by space debris. Regolith on the moon is typically 10 to 15 feet deep, though in some places it can be much deeper, 30 feet or more in ancient, heavily cratered regions. That depth represents billions of years of accumulation. Each impact contributes a little more material. Over time, the layer grows thicker, burying older regolith beneath newer deposits, creating a stratified record of the moon's bombardment history. In younger regions, like the Maria, the regolith is thinner, sometimes only a few feet deep. These areas are younger geologically, so they've had less time to accumulate impact debris. In the ancient highlands, the regolith is thicker because those surfaces have been exposed to impacts for billions of years. This matters for future lunar exploration. If you want to build structures on the moon, you need to understand the surface you're building on. How deep is the regolith? Is there solid bedrock underneath, or does it extend very deep? Can the surface support heavy structures, or will they sink? The regolith could also be a resource. It contains oxygen locked in minerals, potentially extractable with the right technology. It could be used as radiation shielding. Pile regolith on top of habitats to block cosmic rays. Some scientists have even proposed sintering it, heating it until it partially melts and fuses together, to create building materials or landing pads. The dust that was such a problem for Apollo astronauts might actually be a valuable resource for future lunar settlers. The annoying becomes useful when you look at it the right way. The moon's soil contains oxygen locked in minerals, about 40% by weight. Almost half of the moon's regolith, by mass, is oxygen, just bound up in rocks. This is tantalizing. Oxygen is crucial for human survival, obviously, but it's also a key component of rocket fuel. If you could extract oxygen from lunar regolith, you could potentially manufacture breathable air and propellant directly on the moon, rather than bringing it all from Earth at enormous cost. The challenge is that the oxygen is chemically bound in minerals like silicon dioxide, iron oxide, and aluminum oxide. It's not free oxygen you can just breathe. It's locked in stable chemical compounds. Breaking those bonds requires energy and sophisticated equipment. Several experimental technologies are being developed to do this. Some use electrolysis, passing electric current through molten regolith, to separate oxygen from other elements. Others use chemical reactions with hydrogen or carbon monoxide. The processes are energy intensive, but if you have solar panels providing electricity, it becomes feasible. Imagine a lunar base that produces its own oxygen from the surrounding soil. No need for constant resupply missions from Earth. Astronauts could stay for extended periods, and rockets could refuel on the moon before heading deeper into the solar system. The moon, which seems so barren, actually contains one of the most precious resources for space exploration: oxygen. It's hidden in plain sight, locked in every grain of dust, waiting for us to develop the technology to set it free. Helium-3, a rare isotope on Earth, is relatively abundant in lunar soil. This has led some people to envision mining the moon for fusion fuel. Helium-3 is deposited on the moon by the solar wind. The sun produces it through nuclear fusion, and it streams outward with other particles. On Earth, our magnetic field and atmosphere prevent most of it from reaching the surface. But the moon has no such protection, so helium-3 accumulates in the regolith over billions of years. Why does this matter? Because helium-3 could potentially be used as fuel for fusion reactors, cleaner and more efficient than most other fusion fuels. A single space shuttle cargo bay full of lunar helium-3 could, in theory, power the entire United States for a year. That's the dream anyway. The reality is more complicated. We don't yet have working fusion reactors that can use helium-3. Even when we do, extracting it from lunar soil would require processing enormous amounts of regolith, hundreds of tons, to get a single kilogram of helium-3. It's spread incredibly thin. Still, some people look at the moon and see an energy resource for humanity's future. Whether that vision is realistic or not, it's interesting that the moon, by virtue of being exposed to the solar wind for billions of years, has accumulated something Earth doesn't have much of. The moon collects things. It's been patient, gathering particles from the sun, one atom at a time, building up reserves that might someday be valuable to us. The moon has experienced volcanic activity more recently than previously thought. Some volcanic features may be only 100 million years old, young in geological terms. For a long time, scientists believed lunar volcanism ended about 3 billion years ago, when the Maria finished forming. But recent high-resolution images from lunar orbiters revealed small volcanic deposits that appear much younger, patches of dark material associated with volcanic vents, appearing sharp and fresh, not heavily cratered. Dating these features is difficult without samples, but crater counting techniques suggest ages of 100 million years or less. That's recent enough that dinosaurs were walking on Earth when this lava last flowed on the Moon. This is surprising because the Moon should have cooled down by then. Its small size means it should have lost most of its internal heat billions of years ago. Yet somehow, somewhere deep inside, there was still enough residual heat, or perhaps heat from radioactive decay, to melt rock and produce small volcanic eruptions. These weren't massive lava floods like the ancient Maria. They were small, localized events, but they happened, which means the Moon was still geologically active much more recently than we thought. The Moon isn't completely dead, geologically speaking, or at least it took much longer to die than we expected. Its volcanic heart beat faintly for billions of years, finally going quiet only in relatively recent geological time. Perhaps there's a metaphor there. Even small bodies, even worlds that seem cold and dead, can hold on to warmth longer than expected, can surprise us with their persistence. The Moon's lack of atmosphere means the sky always appears black, even during lunar day. On Earth, our blue sky is caused by atmosphere scattering sunlight. When sunlight hits Earth's atmosphere, the gas molecules scatter blue light more than other colors, painting the sky blue. At sunset, when light passes through more atmosphere, the blue is scattered away completely, leaving red and orange. The Moon has no atmosphere to scatter light. Photons from the sun travel straight through the vacuum and hit the surface. Light that misses the surface continues into space. There's nothing to scatter it, nothing to fill the sky with color. So even at noon, with the sun blazing overhead, the sky above the Moon is utterly black. Stars would be visible right next to the sun, though the sun's glare would make them difficult to see unless you shielded your eyes. Astronauts describe this as surreal, standing on a brightly lit surface under an intensely bright sun, but with a sky as black as midnight. It violates our intuition, our Earth-trained expectations of what a daytime sky should look like. The blackness is empty in a way that feels vast. There's no ceiling, no dome, no shell between you and the infinite void of space. Just hard vacuum, stretching up forever, swallowing light, revealing nothing. The Moon's sky is honest in a way. It shows you the universe as it actually is, mostly empty, mostly dark, stars scattered like dust across an abyss. Shadows on the Moon are extremely dark because there's no atmosphere to scatter light into them. On Earth, even in shadow, you can see relatively well because air diffuses light. Sunlight bounces around in our atmosphere, reflecting off particles, filling in shadows with ambient light. That's why Earth shadows have soft edges, and why you can see details even in shaded areas. On the Moon, light only travels in straight lines. If you're in direct sunlight, you're illuminated. If you're in shadow, you're in almost complete darkness. The only light comes from sunlight reflecting off nearby surfaces, and lunar rock isn't very reflective. Apollo astronauts reported that stepping from sunlight into shadow was jarring. Their eyes had to adjust dramatically. In deep shadow behind a boulder or in a crater, they sometimes couldn't see their own feet, even though the sun was blazing just a few feet away. This sharp contrast made photography difficult. Photos exposed for sunlit areas showed shadows as pure black voids. Photos exposed for shadows were badly overexposed in sunlit areas. There was no middle ground, no way to capture both in a single image without high dynamic range techniques. The moon doesn't compromise. Everything is extreme, blazing brightness, or near total darkness, with sharp boundaries between them. It's a world of absolutes, lacking the softness and ambiguity that Earth's atmosphere provides. Living there would require adjusting to the stark reality, planning routes to stay in sunlight, bringing lights for shadowed areas, accepting that the lunar environment doesn't accommodate human comfort naturally. The moon doesn't have true moonlight. It only reflects about 12% of the sunlight that hits it. Its surface is actually quite dark. We think of the moon as bright, as providing moonlight that illuminates Earth's night. And it does. A full moon casts enough light to see by, to cast shadows, to create that silvery glow over landscapes. But the moon itself is dark. Its albedo, the fraction of light it reflects, is only about 0.12. That's roughly the same as old asphalt or weathered coal. The moon is darker than most rocks on Earth would be. For comparison, Earth's albedo is about 0.30. We reflect nearly 3 times as much light proportionally. Earth's clouds, ice caps, and oceans are all more reflective than lunar rock. The moon looks bright to us only because it's sitting in intense sunlight, and we're comparing it to the darkness of space. Placed next to Earth, it would look dull and gray. This low reflectivity comes from the nature of lunar regolith, dark basaltic minerals, tiny glass beads that absorb light, iron particles. Billions of years of space weathering has darkened the surface further, creating that characteristic gray-brown appearance. So moonlight is actually sunlight that's been reflected off a dark, rocky surface. Light that's been diminished, filtered, but still bright enough to reach Earth and illuminate our nights. The moon gives us what light it can, despite being a dark world itself. Different parts of the moon reflect light differently, creating variations in brightness that we can see from Earth. These differences reveal the moon's geological history. The bright highlands are made of ancient, light-colored rock called anorthosite, calcium and aluminum-rich minerals that formed when the moon's early magma ocean cooled. They're heavily cratered because they're so old, dating back over 4 billion years. The dark maria are made of basalt, iron-rich volcanic rock that's darker and denser than highland material. They're younger, less cratered, and reflect less light. Fresh impact craters appear very bright, especially when they're recent. The impact excavates material from beneath the weathered surface layer, exposing fresh rock that hasn't been darkened by billions of years of space weathering. These bright patches, called rays, radiate outward from young craters, creating striking patterns. Over time, even these fresh rays darken as space weathering affects them. So the brightness of crater rays can tell us roughly how old the impact is. Very bright, sharp rays mean a geologically recent impact, perhaps only millions of years old. Faded or absent rays suggest much older craters. When you look at the full moon, you're seeing this tapestry of different ages and different materials, all reflecting sunlight differently, creating the patterns humans have been interpreting for millennia. The moon's face is a map of its history, written in brightness and shadow. The moon's influence on Earth may have been crucial for the development of complex life. Its stabilizing effect on Earth's tilt created consistent seasons over millions of years. Climate stability matters for evolution. Life can adapt to almost anything, but it adapts best when conditions are relatively stable and predictable. If Earth's axial tilt wobbled chaotically, swinging from near zero to extreme angles, the climate would lurch between extremes. No seasons at all to nightmarish seasonal variations. Under those conditions, life would still exist. Bacteria are remarkably resilient. But complex life might struggle. Ecosystems need time to develop. Species need time to adapt. Evolutionary niches need time to establish. Chaos makes that difficult. The moon gave Earth consistency. Its gravitational presence acts like a gyroscope, keeping our axial tilt within a narrow range. For hundreds of millions of years, Earth has had stable, predictable seasons. Summer follows, spring follows winter, year after year, epoch after epoch. This allowed life to evolve strategies for dealing with seasons: migration, hibernation, deciduous trees dropping leaves. All these adaptations assume seasons are reliable, will come back, will follow familiar patterns. Without the moon, Earth might have been habitable, but probably less consistently so. The moon didn't create life, but it helped create the conditions where life could flourish, diversify, experiment, and eventually produce intelligence. We're beneficiaries of the moon's stabilizing presence, whether we recognize it or not. The moon has been a timekeeper for humanity throughout history. Almost every culture developed ways of measuring time based on lunar cycles. Before we had clocks or standardized calendars, the moon was the obvious way to mark the passage of time. Its phases are visible, predictable, and regular. You could look up and immediately know where you were in the monthly cycle. Agricultural societies needed calendars to know when to plant and harvest. Religious traditions needed ways to schedule festivals and holy days. Communities needed shared understanding of when events would occur. The moon provided that. The Islamic calendar is purely lunar, 12 months of 29 or 30 days each, totaling 354 days, which means the calendar slowly shifts relative to the solar year. Jewish and Chinese calendars are lunisolar, using both moon phases and solar year, adding occasional extra months to keep synchronized. Even cultures that eventually adopted solar calendars maintained lunar references. Easter is still calculated based on the moon. The first Sunday after the first full moon after the spring equinox. Many traditional holidays and festivals remain tied to lunar cycles. The moon taught humanity to count time, to think in cycles, to recognize that some things return predictably. Before we could measure seconds and minutes, we measured moons. That connection remains in our language, our traditions, our collective memory. The moon is woven into human timekeeping at a fundamental level. The word month derives from moon, a linguistic reminder of the deep connection between lunar cycles and human timekeeping. In Old English, it was monath, clearly related to Mona, moon. In German, it's Monat and Mond. In Romance languages like French and Spanish, the words are different, mois and mise, but they still derive from Latin mensis, which itself connects to lunar cycles. This etymological connection isn't unique to English or European languages. Many cultures' words for time, periods roughly equivalent to months, derive from or reference the moon. It's a near universal human experience, using the moon to organize time. The match isn't perfect anymore. Our modern months range from 28 to 31 days, averaging about 30.4 days, which is close to, but not exactly, the 29.5-day lunar cycle. That's because we eventually prioritized keeping our calendar synchronized with the solar year, 365 days divided into 12 months of varying lengths. But the name remains. Every time we say month, we're acknowledging that ancient connection, that time when human societies watched the moon wax and wane and counted time by its phases. Language preserves history. Words carry memories of how our ancestors understood the world. The moon left its mark not just on our night sky, but on our vocabulary, our concepts, the very words we use to structure our experience of time. The moon's gravitational pull may trigger small changes in earthquake frequency on Earth. The correlation is weak but measurable. This isn't the same as saying the moon causes earthquakes. Tectonic forces are overwhelmingly the primary driver. But when the moon's tidal forces add stress to faults that are already near their breaking point, it might occasionally be the last straw that triggers a quake. The effect is strongest during new and full moons, when the sun and moon align and their tidal forces combine. Statistical studies have found a small but significant increase in earthquake frequency during these times, particularly for large earthquakes. The additional stress from tides is tiny compared to the tectonic forces building up in faults over decades or centuries. But earthquakes often happen when stress reaches a critical threshold, and even tiny additional stresses might occasionally push a fault over that edge. It's similar to how a building might collapse from a final, relatively gentle push after being severely damaged. The push didn't cause the damage, but it triggered the collapse that was already imminent. So the moon doesn't cause earthquakes, but its tidal forces, constantly pulling on Earth, might occasionally influence the timing of earthquakes that were going to happen anyway. Even in this subtle way, the moon affects Earth. Its influence permeates our world, showing up in places we might not expect. Ocean tides, obviously, but also crustal flexing, atmospheric pressure, and perhaps even the timing of seismic events. The moon has dozens of human-made objects on its surface, from lunar modules to golf balls. These artifacts will likely remain undisturbed for millions of years. The Apollo missions left descent stages of lunar modules, the lower portions of the spacecraft that served as launch pads for astronauts' return journey. They're still there, sitting where they were left over 50 years ago. There are rovers, science experiments, cameras, tools, flags, plaques, and even some trash, empty food packages, defecation collection bags, equipment that stopped working. All the detritus of human exploration, abandoned not out of disrespect but out of necessity. Everything left behind meant less weight to lift back to orbit. Alan Shepard famously hit 2 golf balls on the moon during Apollo 14. They're still there. So are the Hasselblad cameras astronauts left behind, no longer containing film but sitting exactly where they were placed. Without atmosphere, without weather, without erosion, these objects will remain essentially unchanged for millions of years. The rover tracks from the Apollo 17 lunar roving vehicle are still visible. They'll persist until the slow accumulation of micrometeorite impacts eventually erases them, a process that will take eons. Future visitors to these sites will find them preserved like time capsules, showing exactly how we explored, what technology we used, even what we ate. The moon has become a museum of human spaceflight, with exhibits that will outlast any museum on Earth. Several nations have intentionally crashed spacecraft into the moon to study the debris plumes and analyze lunar composition. When a spacecraft impacts the moon at high speed, it throws up material from beneath the surface. By analyzing this debris, using spectrometers on orbiting spacecraft to identify what elements and minerals are present, scientists can learn about the moon's composition without physically landing and collecting samples. NASA deliberately crashed the LCROSS spacecraft into a permanently shadowed crater near the moon's south pole in 2009. The impact threw up debris that was illuminated by sunlight and observed by instruments, revealing the presence of water ice mixed in with the lunar soil. Other missions have done similar things, crashing spent rocket stages or defunct orbiters into the moon. Each impact is an experiment, a violent but informative way of probing what lies beneath the surface. It seems harsh, perhaps, to intentionally crash things into the moon, but the moon is constantly being hit by natural meteorites anyway. A few more human-caused impacts, done for scientific purposes, add negligibly to the billions of years of bombardment the moon has already experienced, and in exchange, we learn. We discover water ice in shadowed craters. We map subsurface composition. We gather data that helps us understand not just the moon, but planetary formation in general. The moon, having absorbed countless impacts over its history, accepts a few more in the name of science. China became the first nation to soft land a spacecraft on the moon's far side in 2019. A significant achievement requiring innovative solutions. The far side presents a unique challenge. Direct communication with Earth is impossible because the moon itself blocks radio signals. You can't send commands or receive data from a spacecraft on the far side using conventional methods. China solved this by placing a relay satellite in orbit beyond the moon, in a special position called a Lagrange point, where it can see both the far side of the moon and Earth simultaneously. This satellite acts as a communications bridge, receiving signals from the lander and forwarding them to Earth. The Chang'e 4 mission successfully landed in the Von Karman crater, within the South Pole Aitken Basin, that enormous ancient impact structure we talked about earlier. The lander and its rover, Yutu-2, have been exploring this largely unknown region, sending back images and data about terrain that had never been examined up close before. This achievement represents not just technological capability, but also a shifting landscape of space exploration. The moon, once the exclusive domain of American and Soviet programs, is now being explored by multiple nations with their own goals and capabilities. The far side is no longer completely hidden. We've landed there, driven across its surface, examined its rocks. The moon's most isolated hemisphere is beginning to reveal its secrets. The moon may contain resources that could make space exploration more sustainable. Using lunar materials instead of launching everything from Earth could transform spaceflight. Getting mass off Earth is expensive, thousands of dollars per pound, depending on the launch system. Fuel alone costs millions for a single mission. If you could manufacture what you need from lunar resources, instead of bringing it from Earth, the economics of space exploration change dramatically. We've already talked about extracting oxygen from regolith, water ice from polar craters, and potentially helium-3 for fusion fuel. But there's more. Lunar regolith contains metals: iron, aluminum, titanium. With the right processing techniques, you could manufacture structures, tools, even spacecraft components on the moon. Solar power is abundant on the moon. No clouds, no atmosphere to block sunlight during lunar day. You could power manufacturing operations with solar arrays. The vision is to create a self-sustaining infrastructure where the moon provides its own resources for continued exploration and development. Mine ice for water and fuel, extract oxygen for breathing, process regolith for building materials. Manufacture what you need on site rather than importing it at enormous cost. This approach is called in situ resource utilization, or ISRU. It's not science fiction. It's a practical approach that could make long-term lunar presence economically feasible. The moon, which seems barren, actually offers what we need. Not easily, not conveniently, but potentially. The challenge is developing the technology to make use of what's there. The moon's low gravity makes it an ideal launching point for missions deeper into space. Escaping the moon's gravity requires only about 5% of the energy needed to escape Earth's. This is enormous. Getting off Earth requires tremendous energy. You need powerful rockets, massive fuel loads, and sophisticated staging systems just to reach orbit. About 90% of a rocket's mass at launch is propellant, burned just to escape Earth's gravity well. The moon's gravity is much weaker. You don't need those huge rockets. You don't need to carry as much fuel. A spacecraft launching from the moon's surface can reach lunar orbit with modest engines. And from lunar orbit, reaching deep space requires relatively little additional energy. This makes the moon a potential gateway to the rest of the solar system. Instead of launching everything from Earth, you could launch crew and lightweight supplies from Earth, rendezvous at the moon, refuel using lunar resources, and then depart for Mars or the asteroid belt with a much lighter, more efficient spacecraft. It's like using a mountain as a base camp instead of starting every climb from sea level. The moon gives you a gravitational advantage. You're already partway up the gravity well, already closer to escaping Earth-Moon space entirely. Future interplanetary missions might routinely stop at the moon for refueling and resupply. The moon could become humanity's gateway to the solar system, a practical stepping stone rather than just a destination. Time passes slightly faster on the moon than on Earth due to gravitational time dilation, a real effect predicted by Einstein's theory of relativity. Gravity warps space-time. The stronger the gravitational field, the slower time passes relative to regions with weaker gravity. Earth has stronger gravity than the moon, so time runs slightly slower on Earth. The difference is tiny, about 56 microseconds per day. That's 56 millionths of a second. You'd never notice it in daily life. But it's real and measurable. A clock on the moon would gradually tick ahead of an identical clock on Earth. Over a year, the difference would accumulate to about 20 milliseconds, still negligible for human purposes, but significant for precision measurements. GPS satellites have to account for similar relativistic effects, or their positioning data would drift off by miles. It's strange to think about. Time itself runs at different rates depending on where you are in a gravitational field. There's no universal, absolute time ticking away the same everywhere. Your position in space-time determines how fast your clock runs relative to other clocks. Astronauts on the moon age infinitesimally faster than people on Earth. Not enough to matter biologically, but enough to demonstrate that time is flexible, relative, dependent on gravity. The Moon exists in a slightly different temporal reference frame than Earth. Time flows differently there, just a bit faster, a subtle reminder that time itself is woven into the fabric of space-time. The Moon has no global magnetic field today, but magnetized rocks brought back by Apollo hint at a dramatic past. These rocks contain frozen magnetic signatures from billions of years ago. When rock solidifies in the presence of a magnetic field, magnetic minerals within it align with that field and become locked in place. They preserve the direction and strength of the field like a fossil preserves the shape of an ancient organism. Lunar samples contain strongly magnetized minerals, suggesting the Moon once had a magnetic field comparable in strength to Earth's current field. This would have required a molten, churning core, a dynamo generating magnetism through the motion of liquid metal. But the Moon's small size means its core should have cooled quickly. How did it maintain a strong magnetic field for possibly hundreds of millions of years after formation? That's the mystery. One theory suggests the giant impact that formed the Moon left it spinning rapidly, and the core remained molten longer than expected due to tidal heating from Earth when the Moon was much closer. Another proposes that the core crystallized slowly from the outside in, maintaining convection in the liquid portion longer than simple cooling models predict. Whatever the mechanism, the Moon once had protection. It had a magnetic shield like Earth's, deflecting solar wind, creating its own magnetosphere. And then, for reasons we don't fully understand, the field collapsed. The Moon lost its shield and has been exposed to the solar wind ever since. The rocks remember what the Moon has forgotten. Scientists don't fully understand why the Moon's ancient magnetic field disappeared. The timing and mechanism remain among the Moon's unsolved puzzles. Small bodies cool faster than large ones. That's basic thermodynamics. The Moon's small size suggests its core should have solidified quickly, shutting down any dynamo action within a few 100 million years of formation. But magnetized rocks suggest the field persisted longer than simple models predict, possibly for 1 billion years or more. Some rocks from different ages show different magnetic orientations, suggesting the field was still active, still reversing like Earth's magnetic field reverses periodically. Then it stopped. Sometime between 3 and 4 billion years ago, the Moon's magnetic field faded away and never returned. The core presumably solidified completely, or convection ceased for some other reason, and the dynamo shut down. But the exact timeline is uncertain. Different samples give different ages for when magnetization ceased, and we don't know if it was a gradual decline or a relatively sudden collapse. Understanding this matters because it would tell us about the Moon's interior structure, its thermal evolution, and how small bodies generate and lose magnetic fields. It could inform our understanding of magnetic field generation throughout the solar system. The Moon's magnetic history is written in rocks scattered across its surface, but we've only read a few pages. The complete story awaits future missions, more samples, deeper investigation. The Moon's interior may contain water locked in minerals, not just ice on the surface. This discovery overturned decades of assumptions about the Moon being completely dry. When Apollo astronauts brought back rocks and soil, initial analysis found no water. the moon was declared bone dry, desiccated by the heat of its formation and billions of years in the vacuum of space. But later, more sensitive analysis techniques examined volcanic glass beads from the Apollo samples, tiny spheres of rapidly cooled magma, ejected from volcanic vents billions of years ago. Inside these beads, protected from space, scientists found traces of water. Not much, only parts per million, but definitely water. This water must have been present in the moon's interior when the magma erupted. It was incorporated into the material that formed the moon, somehow surviving the heat of the giant impact, or delivered later by comets and asteroids. The discovery suggests the moon's interior might not be completely dry. There could be water locked in minerals throughout the mantle and crust, present in small amounts but potentially widespread. This matters for understanding the moon's formation. If there's water inside, it changes our models of how the moon formed and how dry or wet the material was that created it. It also suggests another potential resource. Water might not just be at the poles in ice form, but distributed throughout the moon in rocks. The moon keeps surprising us. Every time we think we understand it, new analysis reveals something unexpected. The moon experiences a day that lasts about 29.5 Earth days, roughly the same length as its orbital period around Earth, due to tidal locking. Imagine experiencing that day. Sunrise on the moon is slow and dramatic. The sun appears on the horizon and gradually climbs higher over the course of several Earth days. It reaches its peak, then slowly descends toward the opposite horizon. Sunset takes days, then comes night, 2 full weeks of darkness. For about 14.7 days, you'd have continuous sunlight. The surface would heat up, though not uniformly. Equatorial regions get hotter than polar regions, and local topography creates shadows that never receive sunlight. Then for the next 14.7 days, darkness. No sun, just starlight and earthlight if you're on the near side. The surface radiates its accumulated heat into space, cooling dramatically. Temperatures plunge to nearly 300 degrees Celsius. This extreme day-night cycle creates unique challenges for anything operating on the lunar surface. Solar-powered equipment only works during the 2-week day. Electronics must survive the brutal cold of the 2-week night. Temperature swings stress materials, cause expansion and contraction, create engineering challenges. Some locations near the poles are special, peaks that receive nearly continuous sunlight, and nearby craters in perpetual shadow. These are called peaks of eternal light and craters of eternal darkness. They avoid the extreme cycling, which makes them attractive for future bases. But most of the moon experiences this slow rhythm, day, night, each phase lasting 2 weeks of Earth time. Time itself moves differently when your days are that long. During lunar night, temperatures drop so low that gases would freeze solid instantly. Any atmosphere would literally fall out of the sky as frost. At 280 degrees or colder, almost everything condenses. Carbon dioxide would freeze solid. Nitrogen would freeze. Even helium and hydrogen, the lightest gases, would turn to liquid or solid at these temperatures if there were enough pressure to create them in the first place. This is part of why the moon can't retain an atmosphere. Even if you somehow generated air on the lunar surface, maybe by releasing oxygen from rocks, half of it would freeze during the 2-week night. Every lunar night, your atmosphere would snow out, forming frost on the surface. Then during lunar day, it would sublimate back into gas, potentially creating winds from the day-night transition zones. It would be unstable, cycling, never reaching equilibrium. And gradually, solar radiation would break down the gas molecules, and the particles would escape to space, and you'd be left with nothing again. The moon's environment is hostile to atmospheres in multiple ways. Low gravity can't hold gases tightly. Extreme temperatures freeze them out. Solar radiation breaks them down. It's as if the moon is designed to remain airless. Future lunar bases will need to be sealed, pressurized, completely isolated from the external environment. You can't terraform the moon, can't give it an atmosphere that will persist. You can only create small bubbles of Earth-like conditions inside habitats and spacesuits. The moon resists habitability. It doesn't compromise. The moon's surface gets electrically charged by the solar wind and UV radiation, and this charging can make dust behave strangely, potentially levitating above the surface. During lunar day, intense ultraviolet radiation from the sun hits the regolith. UV photons are energetic enough to knock electrons off atoms, creating ions, atoms with positive charge. The surface becomes positively charged. During lunar night or in shadowed regions, the surface is bombarded by electrons from the solar wind and from Earth's magnetosphere. It becomes negatively charged. Dust particles on the surface acquire the same charge as their surroundings. Like charges repel, so charged dust particles can actually repel the surface and each other. The electrostatic force might be strong enough, especially for the finest particles, to overcome lunar gravity and cause the dust to levitate slightly. This is speculative but supported by some observations. Apollo astronauts reported seeing a faint glow above the horizon at sunrise, possibly caused by levitating dust catching sunlight. The charging would be strongest at the terminator, the boundary between day and night, where charging conditions change most dramatically. If true, this means the moon has a very thin, dynamic layer of floating dust, constantly changing as the terminator moves across the surface during the long lunar day, invisible most of the time, but present, responding to electrical forces, defying gravity in its own small way. Even dust on the moon isn't entirely passive. It responds to its electromagnetic environment, trembles, rises, settles, alive in its own non-biological way. The moon has unique vantage points where Earth remains visible near the horizon continuously. Locations where Earth never rises high, but never sets, just hovering. Because of libration, the slight wobbling we discussed earlier, there are regions on the moon's limb, the edge between near and far sides, where Earth appears to rise and set slightly over the course of weeks. But there are also specific locations where Earth sits right on the horizon permanently. From these spots, Earth would appear as a permanent feature just above the mountains or hills on the horizon. It wouldn't climb high into the sky like it does from most of the near side, but it also wouldn't disappear below the horizon like it does from the far side. You'd have a perpetual view of Earth, always visible but never dominant, hanging there at the horizon like a blue and white marble perched on the edge of the world. These locations combine advantages of both near and far sides. You can see Earth, maintain direct communication with home, watch our planet rotate and show you different continents. But you're also at the edge, close to the far side's isolation, with access to regions that face away from Earth. Future explorers might value these limb locations. They're psychologically comforting. You can still see home, while offering access to the far side's unique scientific opportunities. A compromise between connection and isolation, between the familiar and the unknown. Geography shapes experience. On the moon, your location determines not just what landscape you see, but whether Earth itself is part of your sky. Earth appears about 4 times larger in diameter in the moon's sky than the moon appears to us. A stunning presence dominating the view. From the moon, Earth would subtend about 2 degrees of arc, compared to the moon's half-degree appearance from Earth. 4 times the diameter means 16 times the surface area. Earth would appear 16 times larger than the moon does to us. Astronauts who've seen Earth from the moon describe it as breathtaking. The planet hangs in the black sky, brilliantly colored. Blue oceans, white clouds, brown and green continents. It's immediately obvious that Earth is alive in a way the moon is not, that it's dynamic, changing, beautiful. And Earth goes through phases from the moon's perspective, just like the moon goes through phases for us. When we see a new moon, an observer on the near side of the moon would see a full Earth. When we see a full moon, they'd see Earth in its new phase, mostly dark. But Earth never moves across the sky like the moon does for us. Due to tidal locking, Earth stays in roughly the same position always, just slowly spinning. To show different faces, you'd watch weather systems swirl across the Pacific, watch day and night sweep across continents, watch the seasons change, all from your fixed viewpoint with Earth hanging motionless above. It would be beautiful and probably emotionally powerful. That's home, visible constantly, so close yet entirely unreachable without a spacecraft. Every human who has ever lived is on that blue sphere, and you're here, on this gray world, looking back. The moon preserves a record of the sun's history in its surface material. Solar wind particles have been embedded in lunar soil for billions of years. The sun is constantly throwing off particles, the solar wind. These particles stream outward at hundreds of miles per second, carrying information about the sun's composition and behavior. When they hit the moon, many get embedded in the surface grains of regolith. Over billions of years, the regolith has been accumulating these particles like a sponge. Each grain contains a record of what the solar wind was like when it was exposed on the surface. Different depths in the regolith correspond to different time periods. By carefully analyzing regolith samples from different depths, scientists can reconstruct the sun's history. How has its output changed? Has the solar wind composition varied? Has the sun's activity level, its magnetic storms and flares, fluctuated over geological timescales? This is information we can't get from studying the sun directly. We've only been observing the sun carefully for a few centuries, but the moon has been recording solar activity for billions of years, faithfully preserving samples of the solar wind like a cosmic data logger. The moon is an archive not just of its own history, but of the sun's history, and by extension, of the space environment throughout the inner solar system. It's a witness to changes we could never otherwise know about. Every grain of lunar dust is a time capsule. The moon remembers the sun's past as clearly as it remembers its own. The moon's origin remains debated, with the giant impact theory having some unresolved questions that scientists are still working to answer. The giant impact hypothesis is the leading explanation. Earth was struck by a Mars-sized object called Theia, and the Moon formed from the debris. Computer simulations show this can work, and it explains many of the Moon's properties: its size, its orbit, the fact that it's depleted in volatile elements that would have been lost in the heat of such a collision. But there's a problem. Earth and the Moon have remarkably similar isotopic compositions. The ratios of different isotopes of elements like oxygen, titanium, and tungsten are nearly identical. This is puzzling because Theia should have had a different composition, formed in a different part of the solar system. If the Moon formed mostly from Theia's debris, it should have Theia's composition, not Earth's. But it doesn't. The similarity suggests the Moon is made primarily of Earth material, or that somehow Earth and Theia had identical compositions despite forming separately. Various explanations have been proposed. Maybe the impact was so energetic that Earth and Theia's material completely mixed and vaporized before the Moon formed. Maybe there were multiple smaller impacts rather than one giant collision. Maybe Theia formed in the same orbit as Earth, making them compositional twins from the start. The truth is, we don't know for certain. The giant impact theory works well in broad strokes, but the details still puzzle scientists. The Moon's origin story, even after decades of study, retains elements of mystery. Some scientists propose the Moon might have formed from multiple smaller impacts rather than one giant collision. This could better explain certain chemical signatures in lunar rocks. The traditional giant impact scenario involves one catastrophic collision. Theia hits Earth, both bodies are partially vaporized, debris forms a disk around Earth, the Moon coalesces from that disk. It happens relatively quickly, perhaps over a few thousand years, but what if it wasn't one impact? What if Earth was hit multiple times by smaller objects during its formation, each impact adding material to an orbiting disk, and the Moon gradually accumulated from this material over a longer period? This multiple impact scenario might explain the isotopic similarity between Earth and Moon more naturally. If the Moon formed from material repeatedly knocked off Earth's surface by successive impacts, it would naturally have Earth's composition. It also fits with what we know about planet formation. The early solar system was chaotic, with many objects colliding and merging. One giant impact is dramatic, but multiple impacts might be more realistic. The debate continues. Scientists run simulations, analyze samples, develop new models. Each approach has strengths and weaknesses. Perhaps the truth is somewhere between, maybe one major impact plus several smaller ones, or a giant impact with unusual properties we haven't fully modeled yet. The Moon's birth story is still being written, revised, refined. We know it involved violence and heat and the transformation of planetary bodies. But the exact details remain tantalizingly uncertain. The Moon may help us understand how to protect Earth from asteroid impacts. Its cratered surface is a museum of impact events that could have hit Earth instead. Every crater on the Moon represents a potential catastrophe that Earth avoided, or in many cases didn't avoid, since Earth was being hit too. But Earth's craters have mostly been erased by erosion and tectonics. The Moon's remain, providing a complete record. By studying the size distribution and ages of lunar craters, scientists can reconstruct the impact history of the inner solar system. How frequent were large impacts? How has the impact rate changed over time? Are there periodicities, clustering of impacts, during certain eras? This information helps us assess current impact risks. We can estimate how often Earth might be hit by objects of different sizes based on the lunar record. We can test whether our models of asteroid and comet populations are accurate. The Moon is also a natural laboratory for studying impact physics. How do craters form? How does impact velocity and angle affect crater shape? What happens to the target material? How much melts, vaporizes, gets ejected? Understanding impacts is crucial if we ever need to deflect an asteroid heading for Earth. The Moon's cratered surface is our textbook, showing us billions of years of impact events in perfect preservation. Every scar on the Moon is a lesson, a data point, a warning. The Moon bears those scars so we can learn from them. The Moon's apparent size in Earth's sky is slowly shrinking as it drifts away. Each generation sees a slightly smaller Moon than the previous one, though the change is imperceptible in human lifetimes. Right now, the Moon appears about 0.5 degrees across in the sky, roughly the size of your thumbnail held at arm's length. But 1 billion years ago, when it was closer, it appeared noticeably larger, perhaps 0.6 or 0.7 degrees. 1 billion years from now, if humans or our descendants still exist, the Moon will appear smaller, maybe only 0.45 degrees across. Total solar eclipses will become rarer as the Moon shrinks in apparent size, and eventually they'll cease entirely when the Moon becomes too small to cover the Sun completely. The change is slow, gradual, invisible on human timescales. You can't watch the Moon shrink any more than you can watch a mountain erode. But it's happening, inexorably, driven by the same tidal forces that slow Earth's rotation. Future beings will look at our photographs of eclipses and the Moon size and realize they're looking at a historical record of a relationship that no longer exists. The Moon we see is not the Moon they'll see. Everything changes, given enough time. Even the Moon's appearance, which seems so constant, so eternal, is slowly transforming. The sky itself evolves, though we live too briefly to notice. Humans alive today are among the last who will experience perfectly aligned total solar eclipses, a cosmic coincidence that won't last forever. For the next few 100 million years, total solar eclipses will still occur. The Moon is still large enough to cover the Sun during optimal alignments, but the window is closing, geologically speaking. The Moon has been drifting away from Earth for its entire existence. Early in Earth's history, the Moon was so close that it would have completely blocked the Sun with room to spare. The Sun would have disappeared behind an oversized Moon for extended periods. Now, we're in a special time when the Moon and Sun appear almost exactly the same size. Sometimes the Moon appears slightly larger and creates total eclipses. Sometimes it appears slightly smaller and creates annular eclipses, where a ring of Sun remains visible around the Moon's silhouette. This near equality is temporary. It's lasted for tens of millions of years already, but it won't last forever. Eventually, the Moon will be too far away. All eclipses will be annular or partial. Future observers will never see the Sun's corona revealed during totality the way we can. We're witnessing something rare and beautiful, something that exists only during this narrow window in Earth's history. It's not unique to us personally. Millions of generations before us saw the same thing, and millions more will. But in the grand sweep of Earth's history, this period of perfect solar eclipses is a brief shining moment. We're lucky to live when we do, to see what we see. The moon has mysterious transient phenomena, brief flashes and glows reported by observers for centuries, which might be caused by gas releases, electrostatic effects, or small impacts. Amateur and professional astronomers occasionally report seeing brief, localized changes on the moon's surface. A small area might brighten temporarily, glow reddish, or show other unusual behavior lasting anywhere from seconds to hours before returning to normal. These reports have been documented for hundreds of years. Some are probably misidentifications, reflections, atmospheric effects, optical illusions, but some seem consistent and credible enough that they might be real phenomena. One explanation is outgassing. The moon isn't completely geologically dead. Occasionally, trapped gases from the interior might escape to the surface, creating temporary clouds or glows visible from Earth. Another possibility is electrostatic discharge, static electricity building up and sparking, making dust levitate and catch sunlight. Small meteorite impacts could also create brief flashes. The moon is constantly being hit, and a fresh impact can excavate bright subsurface material or create a momentary vapor cloud that reflects light. These transient lunar phenomena, as they're called, remain somewhat mysterious because they're unpredictable, brief, and difficult to study. You can't point instruments at them because you don't know when or where they'll occur. The moon, even in its apparent stillness, might have occasional moments of activity, subtle, fleeting, barely noticeable, but real. Not everything on the moon is frozen and unchanging. Some things still move, still flash, still surprise us. The moon's influence on Earth extends to subtle effects on the length of our days. As the moon recedes, Earth's rotation continues to slow, making days gradually longer. We've touched on this before, but it's worth lingering on. Every day you experience is longer than the days people experienced millions of years ago. Not much longer. We're talking milliseconds, but measurably longer. In the age of dinosaurs, 100 million years ago, a day was about 23.5 hours long. Go back to when complex life first emerged, 600 million years ago, and days were maybe 21 hours long. Go back to the moon's formation, and days were perhaps only 5 hours long. The lengthening isn't linear. It's been faster in the past and is slowing down as the moon gets farther away, and its tidal influence weakens. But it continues, relentlessly, driven by energy transfer from Earth's rotation to the moon's orbit. Eventually, billions of years from now, Earth's rotation will slow to match the moon's orbital period. At that point, Earth will be tidally locked to the moon, just as the moon is now locked to Earth. The same face of Earth will always face the moon. A day will last about 47 current days. This won't happen for a long time. The sun will probably die first. But it's the direction things are headed. The Earth-Moon system is slowly moving toward a double-locked configuration where both worlds forever face each other. Time itself, the length of a day, is not constant. It's shaped by the moon's presence, by the gravitational dance between two worlds. The moon remains one of the most accessible yet mysterious worlds we can explore. Despite decades of study, each new mission reveals surprises. We've sent dozens of missions to the moon. We've landed humans there 6 times. We've brought back hundreds of pounds of samples. We've mapped its surface in exquisite detail, measured its gravity field, analyzed its composition, probed its interior with seismometers, and yet mysteries remain. The far side's composition differs from the near side in ways we don't fully understand. The exact state of the core, liquid, solid, or partially both, is still debated. The origin of the magnetic anomalies and lunar swirls isn't settled. The extent of water ice at the poles is still being determined. Recent missions keep finding unexpected things. Water is more widespread than we thought. Volcanic activity persisted longer than we expected. The internal structure is more complex than simple models suggested. The moon rewards close attention. Every time we look more carefully with better instruments, we discover nuances and complications we missed before. The moon isn't simple. It's not a solved problem. It's a world with depth, with layers of complexity, with secrets still hidden. And it's close, only 3 days away by spacecraft, closer than any other world. We can go there, can study it directly, can answer these questions if we commit to doing so. The moon waits patiently. It's been waiting for billions of years. It can wait a bit longer while we build the missions to unlock its remaining mysteries. The moon's phases, waxing and waning, growing bright and fading dark, have influenced human culture, psychology, and mythology since before recorded history began. Every culture that looked at the sky noticed the moon's changing appearance. Some saw it as a god dying and being reborn. Others imagined it as a bowl being filled and emptied. Many tied it to cycles of fertility, agriculture, menstruation, and time itself. The moon became associated with change, cycles, transformation. Unlike the steady sun or the fixed stars, the moon visibly transformed night after night. It was dynamic, mysterious, feminine in many traditions, associated with water and tides and emotion. Myths explain the phases: a celestial creature eating and then regurgitating the moon, a battle between light and darkness, a cosmic cycle of death and renewal. Before we understood orbital mechanics, these stories gave meaning to what we observed. Even now, when we know the phases result from the moon's position relative to the sun and earth, they retain psychological power. Full moons feel different to many people, even if studies don't show clear behavioral effects. The moon still captures imagination, still evokes wonder. We're no longer mystified by the moon's changes, but we're still moved by them. The waxing crescent after new moon feels hopeful, like beginnings. The full moon feels powerful, illuminating, exposing. The waning moon feels contemplative, turning inward. The moon doesn't just light the night. It gives rhythm to darkness, creates a calendar in the sky, reminds us that change is natural, inevitable, and cyclical. The moon remains our closest neighbor in space, our most familiar companion beyond Earth, and yet it still holds mysteries waiting to be discovered. Despite everything we've learned, despite all the missions and samples and studies, we've barely begun to understand this world that's been watching over Earth since before life existed. Every night, when you look up, you're seeing a place that 12 humans have walked, a world that billions more have wondered about. You're seeing ancient lava plains and impact craters, frozen ice in eternal shadow, and magnetic anomalies we can't explain. You're seeing a history written in stone that stretches back to the solar system's violent youth. The moon is old beyond comprehension, yet it's also young in its exploration by humans, young in our understanding of it. We've mapped its surface but haven't explored most of it. We've sampled its rocks from a few locations but haven't visited the poles, the far side's great basins, the mysterious swirls, the deep lava tubes. Future generations will return to the moon, not as brief visitors, but as residents, as explorers, as scientists building bases and conducting research, and perhaps eventually calling it home. They'll answer questions we've posed and discover new mysteries we haven't imagined yet. The moon has been patient. It's watched Earth transform from a molten ball to a living world. It's watched life emerge, evolve, spread, develop intelligence, build technology, and finally reach back to touch it. And it's still there, still waiting, still holding secrets. When you see the moon tonight, or tomorrow, or next week, remember, you're looking at our companion, our teacher, our archive, our future. You're looking at the one place beyond Earth that we've actually reached with our own hands. The moon reminds us that some things are both familiar and mysterious, both close and distant, both understood and unknowable. It's been there all along, quiet and patient, reflecting light on our nights, pulling on our oceans, stabilizing our world. And it will be there long after we're gone, still orbiting, still watching, still silent. A witness to Earth's story, whatever that story becomes. We've traveled through 100 facts about the moon tonight, 100 pieces of knowledge about that familiar light in the sky, each one revealing something about this world that's been our companion for billions of years. Perhaps you've learned something new. Perhaps you've remembered things you once knew. Perhaps the facts have blurred together into a gentle understanding that the moon is both simpler and more complex than it seems. A gray, cratered world, yes, but also a place with ice and lava tubes and magnetic mysteries. A place with history and potential. A place that's shaped Earth and been shaped by it in return. The moon will be there tomorrow night and the night after, continuing its ancient orbit, indifferent to whether we're watching or sleeping, learning or forgetting. It's been there for 4.5 billion years. It will be there for billions more, slowly drifting away, slowly changing, but always our companion. Thank you for spending this time looking at the moon with me. May your sleep be peaceful, your dreams gentle, and may the moonlight, if it falls through your window tonight, remind you of all the things we don't yet know, all the mysteries still waiting among the stars. Good night.